That's perfect. All right, hello everyone to the third instance of Reveal, where this year we're going to talk about bandits and reinforcement learning from user interactions. So I'll start by giving just a quick introduction to the workshop and how we are going to handle things this year in this virtual setting. And then we'll kick things off with a talk from Amit Sharma from Microsoft. So first of all, we've kind of evolved the subtitle of Reveal over the years. So we started that workshop about 3 years ago, really focusing on offline evaluation for recommender systems. So basically looking at traditional recommender systems metric like RMSE and DCG and all of these different offline metrics, and asking the question as to whether we can do better. And in particular, can we find metrics that are more correlated with what you would expect if you were to actually deploy that recommendation algorithm in front of an end user. So in this workshop, so lots of things came up, both in more like standard evaluation techniques for recommender systems, but also looking at off-policy evaluation as a mean to try and get better correlation between offline and online setup. So we decided to focus the second instance, which was in Copenhagen last year, really on that particular aspect. So the relationship between off-policy evaluation, robust estimation, reinforcement learning in the context of recommendation algorithms, and trying to see whether all of these different techniques can be used to find better correlation between the performance you would expect online and what you see offline. And this year we're following that same trajectory just one step further. So basically looking generally at bandits and reinforcement learning for interactive systems. Not only from an offline evaluation standpoint, so not only in trying to understand how good a policy is, but also in trying to develop such policies as well, and trying to understand how can we build better recommendation algorithms by using techniques borrowed from the bandit and the reinforcement learning literature. So we've had a tremendous amount of interest this year. So we have 900 registered participants for the day, which is super exciting. So thanks a lot, everyone, for the interest. Just a quick round of introduction for the organizers. You'll get to meet a lot of us throughout the day because we'll be chairing the various sessions. So Forsten Joachims from Cornell University, Maria Dimakopoulou from Netflix. Hi, Maria, she just joined. Olivier Koch from Criterion, myself from Netflix, Flavian Vassil from Criterion, and Adif Swamanithan from Microsoft Research. So yeah, and I would personally like to thank all the organizers for putting together that workshop for the last 3 years. It's been fantastic working with all of you. So we have a great lineup for today. And in particular, we have 4 invited speakers. So we'll have Inbar Naor, who leads the algorithms team at Tabula, and will be talking to us about offline evaluation for recommender systems. We have Hussam Nassif, who is a senior machine learning scientist at Amazon, and who's going to talk to us about inverse reinforcement learning and its application to recommendation systems. We have Amit Sharma, who's going to talk in a few minutes about causal inference for recommender systems from Microsoft. And then we'll have Min Chen from Google. Min actually talked at the very first instance of Reveal and is coming back this year to talk to us about new developments in bandits and reinforcement learning algorithms for recommendation systems at Google. And we'll hear from her a little bit later in the day. So the agenda is available both on Whova and on the main workshop website. I briefly highlighted it here, and we are going to divide it in 3 sessions with different chairs for all the sessions. So Olivier and I will be chairing the first session, which will start with Amit and then move on to Utah and Bichen's talks. And then we have a poster session, and I'm going to describe a little bit how we are going to organize the logistics of that. And then we will move on to the second session, which is going to be chaired by Flavien and Olivier, with Inbar and Hussam's talk and a panel in the middle. And then we'll move on to the third session, which is going to be chaired by Maria and Adif, where we'll hear from Minmin, Gökhan, and Othman. So on the poster sessions, we're going to use GatherTown. So you might be familiar with it because that's the same platform that RecSys was using, the main track was using for all the poster sessions. It's basically a multiplayer game, except that instead of, I don't know, doing whatever you do in games, you basically visit posters, so way more interesting. And the only thing that we would say, so the link is here, we'll post it in Whova as well at the time of the poster session. Please do not share it publicly. And the discussions in the poster session won't be recorded. So the workshop itself will be recorded, but not the discussions in the poster. Another quick call out, so we have a lot of participants today, but the number of active users we can have at any single point in time in GatherTown is limited. So please, if you're not actively using GatherTown, please just log out and come back in whenever you're ready to engage, so that we can get around some of these limitations. All right, if you need any help, please check the Whova chat. In general, please use the Whova chat and the Whova Q&A section for any question that you may want to ask the presenters. We'll relay all these questions over to the presenters. And please also refrain from using the chat functionality in Zoom as well, and use the Whova chat instead, if at all possible. And one last link to the workshop website. And on that note, I'm going to stop there and hand it over to Amit. Amit, do you want to start sharing your slides?
Yes, let me do that.
Sounds good, thank you.
All right, thank you so much for inviting me. Are people able to see my screen?
All good.
Yes.
Great, so let me just minimize this part. Let's see. All right, so as Wais was saying, I work at Microsoft Research. And today I'll talk about how causal inference can be a useful tool for understanding recommender systems. Now, all of us are familiar with claims about the impact of a recommender system. On the one side, you have claims which are truly amazing. So for example, YouTube and Netflix claim that about 70 to 80% of all videos watched come from their recommender system. At the same time, there are also concerning claims as well, which talk about the echo chamber or the great radicalization that perhaps is happening through YouTube, right? And if you look at both of these claims, both of them are exaggerations, right? And the truth probably lies somewhere in the middle. It's not likely that 80% of views are being influenced by recommenders. At the same time, it's not likely that YouTube may be the great radicalizer, right? So what do we do, right? So in general, there are many metrics that recommender systems are evaluated on. You can evaluate the accuracy. So you can say, is the predicted rating similar to a user's rating? You can see the number of clicks, or you can see coverage. So coverage would say, out of all the items, are there any items that are being excluded? So are you being having any popularity bias or not? And then there's also diversity, which is just simply saying in a list of recommendations, are they diverse or not? But the issue is that these metrics are insufficient for the questions that we want to answer about recommender systems today. So you might want to ask the classic question, does it increase revenue? You might want to ask, does it shape what people buy or consume? Or you could also ask a much more bigger question on whether they're creating echo chambers or making people more polarized. But let's not go there. I think let's just take a very simple example. Some people call it the Harry Potter problem. So what I did just before this talk was to go on Amazon and search for these two books. First, I searched for Harry Potter 2. These are the recommendations I get. These are other Harry Potter books. Similarly, I searched for The Road by Cormac McCarthy, and I got recommendations for other books by Cormac McCarthy. So you can have this strange situation where I can build a recommender that just recommends the next book by the same author And you'll find that it has high accuracy. Users most likely will click it. It'll have high coverage, and it'll also have high diversity, assuming that the users themselves are browsing a diverse set of books. So what gives, right? And so today I'll talk about a causal view of a recommender system that helps us avoid these sort of simple gotchas, but more interestingly, also tells us something more interesting about what the recommendation system is doing. So for example, if you're interested in understanding the impact, you can just take it to a causal language by saying that the recommendation algorithm is a policy or an intervention. So you might have heard economists talk about policies or interventions. And here you can just think of it as the probability of a recommendation given some user context. And evaluation then simply becomes the causal effect of that intervention. And here I'll be using the do operator. If you're not familiar, it just means what would happen if you change the recommendation to something else and looked at the outcome. And the key question for us then should be that what would be the outcome metric in a world without the recommendation algorithm? You can also swap it for in a world with a different recommendation algorithm, where the real world is the recommendations that were shown, and the counterfactual world in red here are the recommendations that were never shown. And you want to see what would have happened if you did not show recommenders. Now, of course, the red world is hard to predict. And if you can, then you can have a causal impact for any kind of outcome that you're interested in. And I just learned that today, many of the talks will be on bandits and RL. So you can also think of this causal impact as the sort of right kind of reward signal that you would want to be learning from any sort of online system. What's the benefit? Here's a sort of small menu of what you can do if you start thinking in terms of a counterfactual world with and without the recommender. Accuracy becomes increase in clicks or revenue. So you no longer care about whether user clicks. You care about in your system, are those clicks leading to more revenue or more number of engagement? Similarly, you won't care about coverage. You would actually care about fairness by parity. And fairness is a causal concept, which is saying that are you being fair to all the items and all the merchants in your system? And similarly, diversity would become fairness by equal opportunity. It simply means if some product is relevant for a user, then it should be shown at equal probability to other relevant products as well. And this is nothing new. I think there's a very interesting paper from 2004 on evaluation of recommender systems where Harlocker et al. Say that recommendations should help the user find a surprisingly interesting item they might not have otherwise discovered. So all of this is known. It's just that so far we lack the tools to measure such counterfactual metrics. So in today's talk, I'm going to talk about a recipe for estimating causal metrics. So I'll talk about a case study. So we'll just go through the recipe through an example of estimating the impact of Amazon's recommendation engine. And in the process, I'll describe the 4 steps of causal analysis. The first thing is that we have to model the causal mechanisms in our system to the best of our ability. Then identify what is the correct metric to estimate. As we'll see, this is the meat of the problem. Knowing what to estimate is really important here. And then we also then check robustness of the estimate to unobserved confounding once we have estimated the metric. And at the end, I'll just pause to talk about how this can be used for other questions as well. I'll just point to resources. I may not get time to talk about it. And finally, I just want to also plug DoI, which is a Python library that I have co-built, which actually implements these 4 steps and makes it easy for you to do causal analysis. All right, so let's take the simplest first metric that I talked about. We are interested in increase in clicks or revenue. So if I'm looking at Amazon's recommender system, I can ask the question, how many new clicks or additional clicks does the recommender system bring? So for example, again, we have the road example, and a book that's recommended is No Country for Old Men, also by the same author. So what do I mean by that? I mean that if you had done an experiment where you randomly exposed some people who went to this page to recommendations and some people to 0 recommendations, then what would be the total number of clicks in both these systems? Ultimately, this is what you care about because you're investing in a team that is building these recommendations, and you're probably also investing in improving them, right? But experiments, of course, are a costly way to monitor a system. This would mean that you're losing revenue each time you don't show these, and you'll have to do this over and over again. The one question we can ask is, can we develop some kind of an offline metric that helps us track this over time? All right, so if you want to do that, then you have to start thinking in terms of a causal model and try to understand what is it that is the counterfactual world to be estimated. So let's go through the 4 steps I mentioned. The first step is we have to model the causal mechanism and identify the confounding factors. So in this case, I'm using a causal graph where what the node represents a variable and an arrow says that here demand causes visits, right? And gray nodes are unobserved, all rest nodes are observed. So here you can draw a very simple graph which says that there is some unobserved demand. You don't know what it is, but you know that that causes people to visit the book roads. That then leads to a recommendation. So this arrow really is the recommendation system's contribution, which leads to a recommendation visit. But then it's not that easy, because it could be that there is also demand for No Country for Old Men as well from the same user. And most likely these are correlated because they are by the same author, right? So just because these books are by the same author, you have reasonable doubt to assume that the demands would also be correlated, and that's the crux of the problem. Immediately, just by having a model of the system, you can make one conclusion, which is surprisingly still not that obvious, that the observed activity, which means if you're just reporting the fraction of clicks made by the recommendation system, it's almost surely an overestimate of the true effect. Why do I say that? You can just simply think in terms of the blue world, where of all the clicks, some are by the recommendation system, some are just convenience clicks. I like this author, I see his book, I will just click on it, right? Why not? And so in a world where there's no recommender, you might just see those clicks as well. And our question is, how can we get the light blue part of this bar graph? So step 2 is the most interesting one. Once you have modeled it, you now want to ask, is there any way to recover the causal effect? Of course, we talked about the naive way, which is you just do the expected value of y divided by x. That would not work, because that also includes convenience clicks. So the second thing you can think of is something like the backdoor criterion, or if you're familiar with inverse propensity weighting, it's exactly that. So you can think of, sure, there is some correlation between the demand of different products. Obviously, we cannot just simply compare the number of clicks, but what if we weight the data based on how likely a user is to have correlated demand, right? So here, for example, you can say that I'm going to calculate a weighted average of the clicks. And the weight is simply given by how likely this user is to have interest in this author. Now, this can work, but one of the limitations is that this method itself depends on accurately capturing some unknown user context, right? So it will always be some kind of an approximation and a faith that you have to put in the variables that you are measuring. And so ideally, we'd want in a metric to not depend on these things. So what can we do? It turns out now's the part where you have to really think about the system that you have and find out the weaknesses it has in terms of what you can estimate out of it. So in our case, we had Amazon's system, and one of the sort of quote unquote weaknesses we found was that it actually gives us not just the recommender visits, it also gives us direct visits to that same product. Which means that if you had this recommended book, at any point of time, you can see how many people are recommended that book, and that's why they clicked on it, and how many people just found it through, let's say, Google search visits or direct browsing and just landed on that page. And it just turns out that just having this additional auxiliary outcome completely changes the problem. And now something that was hard to estimate becomes estimable, as I'll describe. Our graph now changes to this, where the only change is that there is a direct visits to Y. And if you just think intuitively, right? I mean, at this point, you can just start thinking of why would this kind of a direct visit matter? Well, simply this direct visit is a proxy for the unknown demand of this product, right? So if you're finding that recommendation visits are going up, but the direct visits aren't, then that's a clear signal that recommendations are leading to more clicks. Let me give you an example, just make sure what I mean by this. Let's say you have some data set, you don't know which products are actually having those recommendations that matter. So what you do is you just search through your logs and find the products that are having a huge shock in their visits. So maybe let's say John Stewart just recommended a book, right? And that was Cormac McCarthy. What you can then see is whether the recommended books, out of all the recommended books, whether those books were also experiencing a shock at the same time. So in this case, we find that this other book is not having any shock in its direct visits. So what's really happening is that one book has high demand, the other book has no demand. And then if you see that recommendation visits are also spiking, you can intuitively think that, okay, this has to be because of the recommender. And at the same time, if the reverse is happening, you have two books and both of them you find are having a shock at the same time, then most likely it's not to be trusted, the recommendations that are being given, because it could be equally likely that these bulk of recommendations are also just swept up into the direct visit. So that's the idea. The simple idea leads to a criterion called the split door criterion, which generalizes to say that, of course, shocks are a special case, but all you need is that the observed visits through a recommended link should be causal when X is independent of YD, which means that the visits to the focal product, this thing on the left, should be independent of the direct visits to the recommender. So it's literally saying there's a proxy for demand for a product is independent of the proxy of demand for the recommended product. And this directly converts to a method as well. You can now search through system logs for every X and Y product pair, X test if the observed outcome is independent of the cause. If it is, then only estimate the metric on those visits. So we haven't really changed the metric. All we have said is that we're still calculating the fraction of recommendations, but we're only capturing on those pairs where we do believe a causal effect is achieved. And of course, more formally, if you can refer our paper, this criterion can be proved to have recovered the causal effect as long as there is an unobserved demand that is correlated between the different products. All right, so we have step 1 and step 2 done, right? Step 1 was modeling the problem, and step 2 was identifying what needs to be estimated. I'll quickly go through step 3, which is sort of an interesting result that we got with using Amazon logs. So the data that we have is for browsing logs for 9 months. It's about 23 million page views, 2 million users. We got it through consent through a tool called the Bing toolbar, which is like an internet browser toolkit. And then we have about 20K products really, which have 10 visits on any given day. So it means that we're only looking at the 20K products who have at least 10 visits. All the others, think of them as host products. All right, so how do you implement this criterion? In our case, we took a time window of 15 days. We thought that was reasonable enough in terms of how often the recommendation system itself refreshes on Amazon. And then for every t equal to 15 days, we look for every pair of product and a recommended product next to it and look at their visits on those days, right? So you can imagine that for every t equal to 15 days, you have an opportunity for a natural experiment, so-called, to occur, where the split door criterion will be satisfied. If it is, then you select it. If it's not, then you throw it out. And similarly, you can now do it for all pairs of products and their recommended counterparts. And so by just doing this over all pairs of products, you will get a selected list of natural experiments that satisfy the split door criterion. And then you can simply calculate the causal effect using the same formula of y divided by x. When we do it, we found some surprising result on the data set that we had. So this plot shows on the x-axis the top 10 product categories on Amazon. Ebooks, toy, and book are the most popular. And on the y-axis are two estimates. The blue one is the naive estimate, which means for all products, you just calculate the fraction of clicks that were recommendations. And you find that it ranges from 15% to 10% and so on, which is sort of quite high, but it's still lower than the estimates given. But when you're only restricted to the items that satisfy the split door criterion, this number goes below 5%. So I think the actual number is somewhere between 2 and 3%, which is a much more sobering number of the effect of recommendations compared to what we hear. But also more interestingly, if you compare just these two metrics proportionally, it is also saying that over half of the recommendations would have happened anyways, which is sort of not that surprising given many of the recommendations that I showed earlier. But it's a cause for thought on what exactly do we want a recommendation system to do, right? In one case, you could argue that that's fine as long as sort of people are clicking on obvious stuff. But on the other hand, you can also start thinking about, now that I have this metric, how do I improve my recommendation system on this causal metric so that I get more interesting recommendations out? And then we also did a study, of course, we couldn't do an experiment, but we did find other people who had done experiments on e-commerce platforms, and they found sort of consistent results to what we are finding here as well. But wait, I mean, this is just an offline study, right? I mean, you're just believing that we were able to find this causal effect, but we did no experiment, right? So the fourth step is the most critical, in which now we have to look at the robustness of this estimate to some confounding that was missed. And the question that plagues every such study is that what if there was an unobserved confounder that could have affected both the recommendations and the original product, but somehow did not affect the direct visits, right? So here there are sort of a toolkit of different methods you can use. So here I'm showing you one method that we did, which was we selected plausible values for this confounder and then simulated how robust the estimate would be. And as you can see, the estimate changes, of course, but it still lies within the range below 0.05. So that gives us some confidence into what we are estimating. To summarize, this was a project that I did a couple of years back, but what I've seen is that the same process of causal analysis can be applied to develop metrics for new problems, and especially the kinds of problems that are coming up these days. So we did a separate study on checking whether a system provides the same accuracy or performance across demographics. So again, at one point, this may seem just like a conditional probability question. You just condition the accuracy based on different gender, for example. But it turns out that this is also a causal problem because you have to look at what kinds of queries people are doing and what are the differences in their own behavior as well. And similarly, you can think of long-term outcomes that cannot be measured by randomized experiments. And you can also think of new kinds of questions that are coming up in recommendation systems. For example, you have some new product, you want to send recommendations, but you can't just send recommendations to everyone, right? So how do you select the people so that the causal effect of those recommendations is maximized? That's it. I would like to thank again for inviting me. I'll just add that if you're interested in causal inference, we have created a library that you can try out that's much more general, that it implements these 4 steps. And there's also an upcoming book on causal inference that I'm writing with RecSys that you can have to look at this link. All right, thank you.
Awesome. Thank you, Amit. While we ask questions, maybe I'm going to ask the next speaker, Yuta Saito, to start presenting as well so that we're ready to go for the next presentation. But Amit, there's a couple of questions on the Q&A. One is by Andrea. Wouldn't all the evaluation be affected by how well you can do step number 1, designer bias, and any advice in modeling the world? So basically, with the impact,
that's true.
The impact of your causal graph on whatever results you're getting.
That's a great question. Yeah. So it is true. A lot depends on your first step, on how well you model it. But the secret is that you don't have to model the world. You just have to model for the specific question that you have in mind, which are the relevant variables. So if I may, I think if I'm still sharing my screen, in the model that we had, we put this gray bar and it had unobserved variables, right? These could be hundreds of variables. But the interesting part was that even assuming that there are so many unobserved variables, we were able to get something interesting by the small set of other observed variables we had. So yeah, I think it's important, but I would say you can do still a lot more by looking at what you have as observed, making sure that you also put in the unobserved variables in the graph, even if you don't know them, and then seeing what the benefits of do calculus or graphical models can tell you based on those. The second thing I'll say is that that's why I think the step 4 is crucial. So if you are not sure of what you have built, then you can try to simulate other worlds where your model fails. And often that sort of brings up surprises that then you can use to reframe your model. But I agree.
So one question that's from me this time. So with millions of items, especially in the Amazon example, is there really such a thing as a convenience click that is not incremental? Because what's the likelihood that any given user is going to be aware of the full Amazon catalog?
Yes, yeah. So I think it depends in this case, as I was saying earlier, on what is it that you want your recommendation system to do. So I think we can all agree that books by the same author, especially books in the same series by the same author, are not that optimal, because you can imagine that if those recommendations were not there, you probably could have recommended other books and your user may have stopped with 2 books in the cart rather than just 1 by the same author, right? But this is a hard question to answer because without an experiment, we don't know what is the opportunity cost of these clicks. But I do agree with you. I think we shouldn't sort of stretch this argument too much. So maybe split door is an extreme version where you're completely cautious to remove all convenience clicks, and the naive metric sort of includes all convenience clicks. I think based on sort of what kind of system there is, you may want to be somewhere in the middle.
And one last question by Justin. This analysis seems specific to an item recommender setup, which is typically only one part of a larger recommender system ecosystem. Mm-hmm. How well does this generalize to other more prominent recommendation setup?
Yeah, that's a good question. So I think we haven't tried it with user-based or collaborative filtering type approaches, but I think the general setup should generalize easily because you will just have now the cause, outcome, and the auxiliary variable. And instead of timelines of the products, you would be looking at timelines of users and the products themselves, right? So I haven't tried it, so I don't know how well it will generalize. But I think if you follow these 4 steps, I think you will be able to find out what is the right metric for that setting.
Sounds good. So many thanks, Amit. So yeah, it's a little bit awkward because typically we would be clapping right now, but it's difficult in a virtual setting. So we just have to pretend it's happening. All right, so Yuta, thank you so much. Yuta Saito is our next speaker from Tokyo Institute of Technology, and he's going to talk about a large-scale open data set for Bandit algorithms. Yuta, are you here?
Hello, can you hear me?
Hi, yes, yeah. Can you present your...
Also, could you see my slides?
Yes. Yeah, all working fine, yeah.
Also, could you see my virtual notebook? I will do some demonstrations during the...
Yes, yeah.
Oh, great. Okay, let me start now. So hello, everyone. My name is Yuta Saito. I'm an undergrad student at the Tokyo Institute of Technology, Tokyo Tech. And today, I'm gonna talk about my paper, ongoing project, promising project, large-scale open data set and pipeline for Bandit algorithm. I add some modification to make the title more relevant. But yeah, this is the joint work with great collaborators, including Shunsuke Aihara, Megumi Matsani from the ZOZO company in Japan, and also the Yusuke Narita, a professor at the Yale University. So yeah, this is a trace I outline. I would like first share the overview of policy evaluation in the contextual Bandit setting just briefly, because I know you as experts in policy evaluation and causal inference stuff, because this is a review workshop. So I'd like just to make sure we're on the same page. I will share the notation and formulation of policy evaluation in the contextual Bandit setting just briefly. And then the main part is about our open Bandit project, consisting of dataset release and also the pipeline implementation. So first, I will introduce the overview of the dataset and pipeline, and then I will show some example analysis demonstration using the data and pipeline. I have prepared a Jupyter notebook code for this presentation. And finally, I'd like to share some limitation and future work. This is because this is a ongoing work. We are now continue to improve the project. So I'd like to share some limitation and future work in the last part of the presentation. And before starting the presentation, if you're interested in the presentation slides are now available on my personal website. So you can go to my website and then you can have access to the presentation as well. And also you can see my other related work, including policy evaluation and recommender system. Okay. Okay, so let me start the introduction part of the presentation. So we often use machine learning to make decision, just not to make prediction. For example, in this hypothetical recommender platform, the platform decides which items to show a coming user to maximize the expected revenue. For example, they might want to maximize the expected number of conversions, or they might want to maximize the expected number of clicks, right? So this kind of, the machine learning for decision making, say the Bandit algorithm or the reinforcement learning algorithm, have been applied to many applications in industry and also social science or public policy, public health. For example, the news recommendation by Yahoo, and also we have music or a podcast recommendation by Spotify, the artwork personalization by Netflix. I attended yesterday's great expo from Netflix researchers, and they use contextual binary algorithm to optimize the artwork personalization, and also the advertisement optimization by criterion, and also this kind of topics is expected to be applied to the personal businessing or personalized education. So in these in industrial or social applications of the machine decision making, we often want to evaluate the performance of a new decision-making policy using only historical data generated by behavior or past policy. So let me give you a simple example. Suppose you are a data scientist running a recommender system, and you might want to deploy a new policy, new decision-making policy using a cutting-edge deep neural network example, network policy. But you want also to estimate the performance of the new policy before deploying it to the real system. Then you can use the past policy, the data from the past policy. For example, the policy which might be dependent on the more simpler methods, such as the logistic regression method. So this is the central motivation of the policy evaluation. So here is a abstract data generating process in the contextual binary setting. We first observe the context vector X from RID distribution, such as a user visit, then a policy path selection action, such as a fashion item, and then the platform observes the reward, which is now denoted as Y, such as a quick indicator, and the policy, decision-making policy interact with the environment again and again, and then produce the Bandit work data, which is very useful for redesigning the system or improves the function of the system, right? And this kind of log data from Bandit feedback is called the log Bandit feedback. So I now denote the log Bandit feedback as D, which is now consists of X, A, and Y. And X is a context vector for individual I, and A is an action choice by a behavior policy, by B, which is a conditional distribution of action given context X, and the Y is the observed reward, which is associated with the chosen action A. So this is the potential outcome notation. So the log Bandit feedback is a size n of observation, including the X, A, and Y, context, action, and the reward. And what we want to do in the policy evaluation is to estimate the policy value or the performance of an arbitrary evaluation or new policy, pi e here. So B pi e is the performance of the evaluation policy pi e. So this is now defined as the expected reward obtained by hypothetically running a new evaluation policy on a real system. So for example, the expected reward can be an expected CTL, click-through rate, by hypothetically deploying a new decision-making policy to your own recommender or ranking system. So I think this is the reasonable definition of the performance of an arbitrary decision-making policy, and we want to accurately estimate the policy value of a new policy. So the accurate estimation of the policy value, or say accurate of policy evaluation, enabled us to, for example, avoid deploying poor performing policies. And also we can identify promising new policies, or we can identify well-performing hyperparameters for defining policies among many candidates if we have the accurate estimation of the policy value, or if we can do the accurate of policy evaluation. So it's very beneficial in the industrial machine decision making. And there are some standard textbook estimators for the policy value evaluation policy. The first method is the direct method, DM. This first estimates the expected reward using arbitrary machine learning method. And then it uses the expected estimated rewards to estimate the resulting policy value. And this is a definition of the direct method. And EN is the empirical expectation about the size and log bandit feedback data. And the direct method has relatively low variance compared to the IPW counterpart, but it has high bias often, especially when the model for the reward is specified. And another standard method for the off-policy evaluation is IPW, inverse probability weighting, which reweights the observed rewards Y by using importance weights, which is the ratio of the evaluation policy and the behavior policy. And yeah, IPW is consistent. It's great. It converges to the true policy value if you have the infinite sample of log bandit feedback data. But it relatively has high variance, especially in the finite case, especially when all new policies are largely different, have a weak overlap. So that's how the approach comes, the W-robust, which uses the direct method, DM as a baseline. And also the W-robust applies the IPW kind of a weighting method to the shifted rewards to correct the estimation error empirically. And by doing this kind of, by using this control variate, the W-robust is now consistent. It also converges to the true value. And then the W-robust is now locally efficient. It achieves the semi-parametric efficiency bound when the reward model is correctly specified. So there are the three standard textbook estimators in off-policy evaluation in the contextual bounding setting. And there are many theoretical methodological advances in off-policy evaluation recent decades. And we have such as some advanced estimators, including switch W-robust, more robust W-robust, and also the recent one, the W-robust with the shrinkage estimator, which was presented at this year's ICML. And also there are many other off-policy estimators or method where we extend the contextual bounding setting to the more general, more complex reinforcement learning setting. For example, we have a double reinforcement learning estimator using the cross-fitting procedure, which was originally proposed in the WT bias machine learning by the great Chernozhukov, MIT. So yeah, it's great, it's fantastic. It seems OP community made great progress and theoretical breakthrough over the years. And it seems we can now apply the off-policy evaluation reliably to redesign our system, your own, recommended system or ranking system or advertising system. It's great. But our team's concerns here is that there are some issues with the current experimental procedures done in every off-policy evaluation paper. So to the best of our knowledge, experiments in every off-policy evaluation so far rely on either of synthetic data or unpublished data. So the one method to do the experiment on off-policy evaluation is to use the free simulation, free synthetic or the multi-class classification data. So I think it's a good way to do experiment because it's easily implementable. And yeah, it's great, but this is also unrealistic because these data are not the real-world bounded data, and also often these data are very small compared to the real bounded data. So it's easily implementable but unrealistic. And the other method to do the experiment on off-policy evaluation or to do the comparison of off-policy estimators is using the real-world bounded data from the industry. But these datasets are often, or I can say always, unpublished to the research community. So this way is realistic, but irreproducible because other researchers cannot reproduce the result of the experiments using the unpublished data. So yeah, it seems we need real-world dataset enabling the evaluation of off-policy evaluation. Yeah, I know that there are some similar datasets enabling the evaluation of bounding algorithm, but there are no real-world data enabling the evaluation of off-policy evaluation or the comparison of different off-policy estimators in a data-driven, realistic, and reproducible manner. So this is our main motivation in our project. The goal of our Open Bandit project is to enable the realistic and reproducible experiments on bounding algorithm and mainly on off-policy evaluation. And for these purposes, we propose an open bandit dataset and open bandit pipeline as two main modules of our open bandit project. So let me now introduce the great project, first open bandit dataset. So we collected the open bandit dataset on the Zozotown platform. This is the largest fashion e-commerce in Japan. And the Zozotown recommendation uses some bandit behavior policy to recommend some fashion items to user. And we collected the log bandit feedback from the Zozotown platform. So we have X, the context vector from the user demographic profile. We have A, the action choice from behavior policy. I will later specify the policy. And also we have the click indicator as a reward. So this is the overview of our data collection process on the Zozotown recommendation platform. So this is the the basic view of the open bandit dataset. We have timestamps. The data collection was done in the November last year. We have item ID and position ID. We have 3 positions in the Zozotown recommendation interface, and which constitute the action set. And the propensity score is the probability of an item or fashion item being presented to a user by behavior policy. And we also have the click indicator. This is the binary reward in our setting. And also we release some features, user-related and also item-related features. So researchers can try their own contextual binary policy on our dataset using the open source feature vectors. Okay, and there are some essential, interesting features of our open bandit dataset. The first feature is that it's large scale. We released over 25 million records of log bandit feedback data collected on the largest fashion e-commerce in Japan, Zozotown. But the most important point with our dataset is that our log bandit feedback data was collected by multiple behavior policies. So specifically the uniform random policy and the Bell-May-Thompson sampling policy, which was pre-trained before the data collection process. And this feature actually enables the realistic and reproducible experiments on off-policy variation for the first time in the literature, we believe. So here is the experimental protocol for doing the evaluation of off-policy variation with our dataset. And the protocol has 4 different steps. The first step is to prepare 2 different log bandit feedback data collected by 2 different bandit policies. So we have now the D1, which is the log bandit feedback data collected by pi1, which might be the uniform random policy in our dataset. And we have the other, the D2, which is the log bandit feedback data collected by pi2, which might be the Thompson sampling policy in our dataset. So this is a step 1. And the next step is to regard one of the 2 policies as a hypothetical evaluation policy here pi1, and also the other as a hypothetical behavior policy here pi2. And then we do the simulation. We do the simulation to estimate the performance of the evaluation policy pi1 by using some off-policy estimators b hat here. So b pi1 is the policy value, our estimate, and the b hat pi1 d2 is the estimated policy value of pi1 using off-policy estimator b hat, and the log bandit feedback data d2, which is collected by hypothetical behavior policy pi2. Right, so this is the off-policy variation simulation. But remember that the task here, what we want to do here is to evaluate the estimation accuracy of an off-policy estimator b hat, right? We don't want to do the off-policy variation itself. We want to evaluate the accuracy of off-policy variation here. And the next step is to do the on-policy estimation. So we do the off-policy evaluation of the policy value of evaluation policy, pi1, and we can regard it as a ground truth policy value. We do this on-policy evaluation or on-policy estimation because we actually have D1 in our dataset. Our dataset contains the log bandit feedback data collected by 2 different bandit policies, right? So the right-hand side is the empirical expectation of the observed reward in D1, which is the on-policy estimation of the policy value of the pi1, right? So, and we can regard it as the accurate estimation of the ground truth. And the final step is to compare the estimated policy value of the policy value of pi1 with the ground truth policy value, which is an on-policy estimation, to evaluate the accuracy of an off-policy estimators, or PE estimators. For example, you can use relative estimation error on this slide, or we can use other measures, for example, mean-scale error or relative mean-scale error to measure the accuracy of an off-policy estimated p hat. And by applying this 4-step, the experimental protocol to several different off-policy estimators, we can compare the accuracy or the estimation performance of different off-policy estimators in a data-driven, realistic, reproducible manner. For example, we can compare the accuracy of direct method IPW and DR and pick the best one using our open-bounded dataset, right? And here it's a brief comparison of a dataset with the existing real-world bounded dataset. There are some similar datasets we know, the Criterion data and the Yahoo data. I think many of you are familiar with the Yahoo data, which was originally proposed or released by the Lee Lee paper about linear contextual boundary application to the Yahoo recommendation interface. But these data have log-bounded feedback data collected by only a single behavior policy. So we can do the evaluation of boundary algorithm using the data, but we cannot do the evaluation of policy evaluation using the previous dataset. But our open bounded data contain the log-bounded feedback datasets generated by multiple different behavior policies, which enables evaluation of policy evaluation for the first time. And also, so this is the most fascinating feature. But another feature is that the dataset comes with the pipeline implementation, which we call the open-bounded pipeline. So in addition to releasing the open-bounded dataset, we implement the open-bounded pipeline, a Python package to streamline and standardize experiment on force evaluation, or force evaluation itself. And if you're interested in the package, the pipeline, please find out the OBP, then you can easily find our GitHub repository. Okay, and this Python package, open-bounded pipeline, consists of 4 main different modules: dataset, policy, simulator, and OPE modules. The first module is a dataset module, and we implemented the dataset loader for, of course, our open-bounded dataset. So you can easily load and pre-process our open-bounded dataset using this dataset module. And the next module is a policy module. We have implemented behavior policies used in the zero-time production. And also we have implemented some online and offline bounded policies. And the next module is a simulator module. This is more optional. If you want to evaluate the performance of online bounded policies, such as the linear contextual epsilon gradient, for example, then you may want to do the replay method proposed by another Lee Lee paper. And so we implement this replay method in this simulator module. So you can use this simulator module if you want to evaluate the performance of online bounded policies. And the last, our final step is of course evaluation. We implemented some of course estimators such as DM, IPW, DR, and also some advanced ones, including switch, more robust, doubly robust, and also self-normalized one in the of course evaluation module. So by combining these 4 main modules, you can do the evaluation of boundary algorithm, and also you can evaluate several different of course estimators in an easy standardized manner. Okay, so let me now run just a quick start example, a demonstration of how to use the, of course, our open-bounded pipeline. Then you can see the basic usage of our pipeline. So I have prepared the Jupyter Notebook code for this presentation. I think you can see the Jupyter Notebook file. So I will now show an example of estimating the policy value of an IPW runner. This is the of-policy learning method, the counterfactual policy, using cost-sensitive classification. And I will do the of-policy evaluation of this IPW runner using the uniform random bucket of our open-bounded dataset and some of-policy standard of-policy estimators. Okay, first I import some important features of the open-bounded pipeline, OBP. I import the dataset module, policy module, and OPE module. Okay, then we implemented the open-bounded dataset class to load and pre-process our open-bounded dataset. I will now specify the uniform random bucket of our dataset. Then we can easily load and pre-process the data. And I will now use a small size example dataset, having only 10,000 example, because this is just the simple demonstration. And the next step is the off-policy learning using cost-sensitive classification based on the IPW loss function. And we implement the class IPW runner. And I will now use the logistic regression from scikit-learn as its base model, base classification model. And following the fit predict interface, fit predict procedure, we can easily predict the action, the new action for the log-bounded feedback data, right? So the counterfactual policy runs a new decision-making, new decision-making rule from log-bounded feedback data, and then predicts the new action choice for the future context. And the third step, the final step, is of-policy evaluation. We implement the of-policy evaluation class to standardize the procedure of of-policy evaluation. And I now set the some of-policy estimators, such as IPW and the self-normalized IPW and also W-robust. And this is a very simple implementation, I think. And we can easily visualize the result of policy evaluation, including the IPW, SN IPW, and also W-robust one. So what I have done here is to evaluate the performance of the IPW runner, which is a counterfactual contextual runner, using some standard estimators and also the uniform random bucket of our open bandit pipe dataset, right? So this is just a simple demonstration. And as you can see in my analysis, we can easily implement the experiments on force evaluation or of force evaluation itself using our open bandit pipeline. So just 10 lines of code is sufficient for doing the standard analysis, standard evaluation of the counterfactual policy using such as IPW, DMODR. So it's great, I think. And also we built a detailed documentation for our dataset and pipeline. So even if you are new in this field, even if you are new in this force evaluation field, you can still learn how to use our dataset and pipeline easily, and also you can learn the formulation of the force evaluation from this documentation. Okay, and finally, we perform some benchmark comparison on basic of-policy estimators using the full-size open-banded dataset. So here is a simple result, and IPW and SN IPW DR seems to be accurate in the of-policy evaluation. But this is, the very simple task. What we have done in this benchmark analysis is to estimate the performance of a context-free, the simple policy using the uniform random bucket. I think this is very simple task in of-policy evaluation. So as a future work, we want to expand the dataset to include some more practical, realistic, difficult of-policy evaluation task. Okay, so finally, let me share some limitation because this is an ongoing project. The first limitation is the assumption on the reward structure. So we now assume that a click of an item, this is the definition of a reward, depend only on the action and the position. So here is the town recommendation. And you may know that this is not a standard formulation of the policy evaluation of boundary algorithm because we have 3 simultaneously presented action in the town recommendation interface. So we have to make some assumption to apply the standard of policy evaluation to our dataset. So our assumption is that the action set can be decomposed into the item set and the position set. So the item set now consists of 80 fashion items, and the position set, we see that the left, center, and right, the 3 positions. So by making this making this assumption on the action decomposition, we can apply the standard of policy evaluation such as DM, IPW, DR easily to our dataset. But it might be strict, because this assumption ignores the possible interaction among the 3 items recommended at the same time in the same recommendation list. So as a future work, we will compare the other estimators relying on other reasonable assumptions, such as we can, for example, compare the standard estimator with the estimators for the straight recommendation setting. I read a great paper from Spotify Research this year, KDD. They studied the counterfactual straight recommendation of policy evaluation. So we may be able to implement the Spotify estimator to our pipeline in the near future. Okay, there are some other minor limitations. The first is that the current data contain only context-free policy, does not use any contextual information. So we plan to run another data collection experiment to expand the dataset to include more useful, realistic bounded dataset. And we hopefully want to release the open bandit dataset V2 earlier next year. And the other minor limitation is that the current benchmark analysis is very simple, just a performance comparison, primitive. So we are now running some comprehensive, extensive experiments to answer some interesting questions in of-policy evaluation, such as can of-policy evaluation estimate the performance of a new policy in the future environment or the outsample policy value? I think it's a general usage of policy evaluation in the industrial setting. And the other question might be, how does the performance of OPE change with different setting? For example, how does the the estimation performance of W-robust change when we use different machine learning methods to estimate the expected reward? So we are now running some experiment to answer that kind of interesting questions. Okay, that's it. Thank you for listening, and please come to a poster. I will attend the poster session, and for further discussions, you may have some suggestions, feedback, or questions for improving the open project. And you also easily access to our resources, GitHub, documentation, and etc. Okay, that's it. Thank you, and we have some time for answering questions.
Awesome. Thank you so much, Yuta. Olivier, can you handle the questions while I set up the next talk?
Mm-hmm.
Oh, I think Olivier. Oh, hello?
Hi.
Okay. I think the sound is breaking up, Olivier, so I'll handle the questions for now. Mm-hmm. So one question, Yuta, how do these new benchmarks compare with the real-world letter 4 datasets from Kin and Liu in 2013 that contain queries to label documents that are often used in contextual Slate Bandit of policy evaluation?
I do not know the data. I will search for it, but yeah. So then I will answer the question. But I think it might not contain log Bandit feedback data from different contextual Bandit policies. So yeah, maybe this dataset can be used for the evaluation of Bandit algorithm or evaluation of offline ranking policy, unbiased ranking rank method. But I think this dataset cannot be used for the evaluation of policy evaluation or evaluation of a threat recommendation set. But I will search for it.
Sounds good. Another question, so very generous contribution to the community. The logging policy was random uniform. Also, is each action a slate or just one item?
Okay, one of the logging policy is uniform random, and the other is fixed behavior, fixed value Thompson sampling, right? So we have now two different logging policies. And the other question is, yeah, action
is each, yeah.
Yeah, yes, right.
Is each, so.
Yes, the action is, yeah, the action is now combinatorial. We have three simultaneous represented action. So we make an assumption on the reward structure to reduce the cardinality of the action set. But if you exactly do the of-course evaluation, then you can address the kind of combinatorial action set.
Awesome, that makes sense. And final question, do the features include some information for differentiating users so that personalized collaborative filtering solutions can be evaluated over it?
Oh, this is not the dataset for collaborative filtering and also a recommender system. It's a dataset for Bandit algorithm. So now the feature information cannot differentiate each user. So you can think of a feature as just environment information. So yeah, we want you to use this dataset for your Bandit research or of course evaluation research.
Sounds good. That's awesome. I think I'm going to stop there for the questions, but Yuta, you'll be available for posters later as well for any chats. But yeah, really nice work. Lots of comments saying that it's amazing. Thank you so much, Yuta.
Yeah, thank you.
So now for the next talk, we have Bishenchi, but she's having some connection troubles. So I have a recording of her talk here. So I'm going to broadcast that recording, and then Bichen will be here for any questions after the end of that. So bear with me a second while I project the right talk. Can you see it? Yeah.
Hello, everyone. I'm Bichen Shi, a postdoc at the Insight Center for Data Analytics at University College Dublin, Ireland. Today, I would like to present our work, a distributed asynchronous deep reinforcement learning framework for recommender systems. Why do we need a distributed reinforcement learning-based recommender system? First of all, mobile devices like phones and tablets are increasingly powerful. I have seen many of them do professional level image and video editing and handle almost all our daily tasks. They can even be used to train machine learning models, and many of the deep learning platforms are moving towards mobile devices. For example, the TensorFlow Lite. Mobile devices also containing an enormous amount of user private data, including internet surfing footprint, shopping lists, recent interest, location, daily schedule, etc., etc. Some of this data can be considered as extremely sensitive and should never leave the device. Generally speaking, the more data the user allowed to share with the recommender system, the better recommendation he could get. But this comes to a sacrifice of privacy. And recommendation service is becoming essential for users to quickly searching for the things they would like to find from a huge option space. However, since the data are private and sensitive, user could be reluctant to share it with the central server. Even with encryption, there is a high risk of private data leaking and misuse during the collection, storage, and transmission when using a central server. It is also a waste of resources if we rely only on a central server when users already have very powerful devices that can be used to participate in the recommendation process. A distributed framework should have better scalability. On the other hand, the recommendation environment is becoming increasingly dynamic and interactive. Candidate items could quickly emerge and die out, while users' interest might shift in just a few minutes, and the user might respond to the recommendation every few seconds. We would prefer a recommendation model that could perform well in such a challenging environment and considering the long-term user satisfaction at the same time, which makes the reinforcement learning approach a good choice. The state-of-the-art related works could fall into three categories. One type of works focusing on modeling the recommender system using reinforcement learning approaches, mostly in news, ads, next-time recommendation scenarios. They studied the problem of the state representation, rewards functions, network structures, policy, the model evaluation of the recommender systems in reinforcement learning settings. Another category focused on making the recommender system distributed using federated learning. For example, these approaches study the way of making federated collaborative filtering approach or federated matrix factorization approaches. Our work is in the conjunction of these two categories. Another type of work that is closely related but not directly involved is the works that focus on privacy preserving in recommender systems. They not only study the privacy risk when using a central server, but they also study the problem of the untrusted central server, the usage of differential privacy, cryptographic, and so on. In our work, we do not directly focus on this aspect, and this could be our future direction. We propose a distributed asynchronous deep reinforcement learning framework for recommender system, aka DADRL. We model the item recommendation and rating prediction as a classification problem, which can be either binary or multi-class. In the binary approach, given a user, an item, and a context, the model classifies it into recommending the item or not to the user. In the multi-class classification scenario, the model can predict the rating the user might give to the item. We use advantage actor critic methods as a base model. One key aspect of the distribution framework is that the user's data are collected and kept on their devices, and are not collected in a central server. The model training is also performed on the local device level, where coordinated by a central server. Only the gradients of the losses of the model have shared with the central server, but not the user's private data. The update is performed asynchronously. This means the user and their devices can join in or leave in the training process anytime they prefer, and is not affected by the online-offline status of the network. In the following slides, I will break down the framework and explain each component one by one. In a reinforcement learning problem, we have an environment and an actor. The actor needs to make a series of actions according to a policy to receive a high cumulative reward. For recommender systems, the environment is the recommendation platform, where the users are requesting recommendations in a certain context. For instance, recommending news articles to readers on a news website. The user request, the candidate item, and the context are captured in the state. And the state is sent to the actor, which is the recommender. The recommender learns a policy and chooses an action, which is recommending the item or not. The user receives the recommendation and gives some feedback, whether he clicks or likes the item. The feedback and the updated state and context are sent back to the recommender. The recommender uses the feedback to learn a value function that helps to improve the recommendation policy. This loop continues until the user leaves the platform. Since the interaction will continue for multiple rounds, the recommender learns to recommend items that could potentially generate more rewards in the long term. For example, recommending high-quality items rather than low-quality but eye-catching items. For news articles, recommending trending news stories with a series of news reports rather than a standalone article. In the original distributed setting, an environment would consist of all users and their data, and all environment on all workers are exactly the same, sharing an equal portion of the dataset. But in our framework, each environment only has one user. This is a one user per device setting. Essentially, each environment is different from the others because the user has a unique preference and clicking behavior. However, one user's data is far from enough to train a proper recommendation model, so we need a central server to coordinate the training on all users' devices. We have a central server that hosts a global recommendation model, aka the policy neural network. There are many local user devices, which could be phones, tablets, laptops, or TVs. Each local device has a copy of the global policy neural network. The steps that happens here is what we have described in the previous slides. A local device trains the policy neural network by interacting with the user and collecting rewards. The loss gradients of the local neural network are sent to the central server every few steps. The global model is updated by the gradients, and the weight of the neural network are sent back to the local devices so that the local device has the most recent policy network. During this process, the user's data remain on their devices, while the candidate item information is sent to the local devices from the server. The synchronization happens at different time points for different devices because some users would interact with the model more frequently than the others. In summary, the training process consists of 5 steps. At the beginning, the global server initiates the model and its weights. The local model is reset to the global model, then it makes a recommendation to the user and receives reward. The local model calculates policy and value losses from reward and gets the gradients from the losses. The accumulated local gradients are sent to the server, and the global model is updated every m steps, and the cycle repeats. We set the reward function to reflect the recommendation accuracy, and this is the loss function we use for the advantage actor-critic model. The model's neural network takes the state as input, has few fully connected layers, and output both the policy and the value. The input state represents the relevancy of an item-user pair, including 4 types of features: user demographics such as gender and age, item details such as title, description, and popularity. The user-item interaction captures the user's browsing history, and the context is the time and the location of the recommendation. Note that the action space of the policy is to recommend the item or not. We do not hard-code the candidate item set into the action space, because the candidate item set might get updated very frequently on the hours level. Using this more flexible approach, our model can better handle the dynamic environment. We compared DADRL against some other methods, including LinUCB, a multi-arm bandit approach, DQN and DDQN, similar to the DRN work. The original A2C and A2C in federated-like setting. The 2 A2C approaches are updated in synchronous style, while A2CF also uses the 1 user per device setting that is similar to our DADRL. We evaluate the click-through rate using a subset of the news click predicting dataset Outbrain. The dataset has 22K users, 400K interactions, and the average user interaction session is around 20. During the training, we recorded the CTR of the 6 models for 20K training episodes. 1 training episode is a full interaction session of 1 user. For distributed methods, we use 5 workers in this experiment. We could see from the figure that DADRL performed equally well or even slightly better than the other methods, regardless of whether they are centralized or distributed. In the test, we use 1 plus k random item settings and averaged the result CTRs of 5 runs. We tested k of value 1, 10, 20, 50, and 100. DADRL consistently outperforming other methods in all k values. It works very well even when k is as large as 100. Comparing the 2 A2C methods, we found the A2CF, which uses the 1 user per device settings, has more advantages. We also tested the model performance using a large number of workers. We simulated the distributed training process on a server with up to 100 cores. Note that Outbrain has 22K users, and it is infeasible to get 22K devices to test our 1 user per device setting. So we distributed the users to up to 100 cores. At any time, there are only 100 users involved in the training process. The workers are reused for other users once the training of previous user is finished. The process is similar to federated learning, which only select a subset of devices for training at each round. The difference is that our process is asynchronous. We don't expect this division of user to the cores to fundamentally affect the asynchronous training process. We measured the training time speed up, which increasing with the number of workers as expected. And the training CTR is not affected by the different number of workers, meaning the performance of the model is unlikely to change if we use even more workers. We also studied the hyperparameter M that controls the local model update frequency. M is essentially the mini-batch size. When training the model, we tested the model every 2K episodes. From the figure, we can see that all 5 models reach their optimal CTR very soon, but later on, for m equals to 50 and 100, the models are overfitting and the CTR is decreasing. We studied the session length of the outbrain dataset, and 3/4 of the sessions are shorter than 20, while 1/4 is between 20 to 50. It seems the best value of m should be consistent with the session length distribution. The update frequency should close to the majority of the session's length to avoid the unwanted impact of the extra long sessions on the recommendation model. For the future work, our framework currently does not support personalization, as the local model is an exact copy of the global model. However, this distributed architecture seems to be a good fit for the personalized recommendation, because the local model only interacts with one user on one device. In the future, we hope to further explore the possibility of a personalized recommendation on top of the current framework. It could be adding a personalized layer to the current network, or even adding another neural network in response to the personalization requirement. Secondly, we would like to further enhance the privacy of the model. For example, using differential privacy by adding noise to the gradients or putting a threshold to the updated weights. We are also concerned with the model poisoning attack. When there are some malicious users in the training process, we might want to consider adding a norm threshold to eliminate the poisoned model updates. We also need to look into an efficient candidate item shortlist approach at the central server side to minimize the amount of candidate item information transmitted to the local devices. And we want to study some other action space representation approach, advanced neural network structure, and feature representation techniques, such as embedding RNN self-attention. Finally, we would like to further explore the better offline training and evaluation approaches that have less data bias. If you have any ideas and experiments regarding these directions, please come to our poster session, and I would be more than happy to further discuss them with you. Here are the references. And thank you very much for your time. Please come to our poster session for more discussion.
Great. Can you hear me now? Yves, can you hear me?
Perfect. Well, now I can't hear you. Olivier? All right, I think Olivier disconnected. Maria, do you want to take over? You're muted. Otherwise, and Bichen, are you here for questions as well? Hello? Oh, I see Olivier now.
Can you hear me?
Yes. So let me.
You should make Maria
Bichen to unmute. Oh, I can. Yeah.
You should also make Maria a co-host.
Hello?
Oh, that's it.
Yeah.
Hello, Bichen.
I can. Hello, hi.
Hi, Bichen.
Hi, can you hear me? Yeah.
Yeah.
Yes. Yves, can you hear me well, or should we ask Maria to do it?
All good.
I can do it?
Yeah.
Okay, cool. Thank you very much, Bichen. We have time for questions. So the first question we have from the audience is, in your network, how are you combining the policy head and the value head?
So they are using a shared network, and the loss would be a total loss of them. So shared network meaning they are sharing same network, but only the last layer they are separated.
So when you do the training, you train both of them together. Yeah, sorry, did you hear me?
Yeah, all good. Olivier?
Yeah.
I think Olivier froze again. So I'm just going to handle the Q&A. And so the other question is, how did you deal with missing data in the data set?
Unfortunately, we don't. So all the data set we test are pretty dense, or at least the user have gathered enough amount of interactions. So it's not really a problem for us.
Sounds good. And the final question, in the evaluation, DQN seemed to do very badly over time, following a different patterns than the other solutions. Do you have any insight as to what might be happening there?
I'm not exactly to be sure, but I could imagine that DQN has, because DQN has more structure and more robust, so I guess that could be one of the problem. And generally testing, we found that some algorithm may randomly do such things, but DQNs usually is not as good. So I guess it's because the structure of the model. Yeah.
That's super interesting. Sounds good. Thank you so much, Bishen. So we're almost at time. So I think we're probably going to use the next few minutes to leave enough time for everyone to join the poster session. So the link is on Whova, and I'm going to post it in the Zoom chat as well, just to make sure it's everyone has it. So please feel free to join the poster session, and all the presenters as well will be available in the poster session today. So if you have any other questions we didn't get to, please feel free to join. And see you everyone in a few minutes at the poster session. It's going to start at past. See you in a bit.
Hello?
Hi, Olivier.
Hey, Maria, do you hear me?
Yes, I can hear you fine. How are you?
Good, doing well, thanks. Are you enjoying the workshop so far?
Yes, very much. Gather Down is awesome. You know,
Great, thanks.
I will miss that.
So did you, are we connected with other people? Where is Eve? Is Eve here or? Is it
I
just
hear you too. If you guys can hear me.
okay. Everybody's here, right. Okay.
Yeah.
Hey, Edith.
Hey,
There's 128 participants online.
Right.
Ooh.
Yeah, so sorry that
Okay.
I think the sound, like my connection is not great. So I can't really do the Q&A session, Eve. Very sorry.
No problem.
It's
It
not
looks
super-
great. It sounds great now, though. So
Yeah,
oh,
let's try. I'm sharing this one, right, with you, I think? Or
with Flavian.
Flavian.
But
With
Flavian
Flavian.
was in the middle of a deep conversation at the poster session. So I don't know.
Okay.
You might
Well,
have to
he's gonna be
get
kicked out
Inbar
by the
started.
system anyway. But
Hopefully.
yeah, yes. Let's try to share together. If it doesn't work, I think he will do it by himself. But I'll be around. Yeah.
Sounds good. And
Did you-
is Inbar here as well? I saw her on the Gaverton, but she might still be chatting with folks.
Okay. Yeah, we have still a few minutes left on Gather Town. But yeah, I think it's been working.
Oh, I was going to say, Maria, should we just briefly sync during the next poster session to figure out how to chair the final session?
Sorry, if I didn't catch that.
Oh, I was asking
Maria
Maria if we can just briefly chat during the next poster session to figure out how to chair the final session. I think it's Maria and me who are up, right, for the final session.
Yeah, for the final session. And Maria, can you unmute yourself? Does it work?
Yeah, it works.
Yes, perfect.
Okay, yeah.
Nice.
There are two me, one a guest and one co-host.
I see.
That was a problem before.
Yeah, I noticed like I'm having like at least 2 Hoover windows open and the Zoom call open because I'm also trying to monitor the questions that are going on. So that's on a different, like, need to go into the session. But
Yeah,
I
same
also
for
find
me.
it useful to have the overall agenda too.
I'm back. I was discussing and I saw people leaving and I was like, okay, maybe it's time to.
Yeah, usually in the real world, you'll see a bunch of people moving, but that's not the case here. So
yeah, exactly. I was
you
like,
don't get
okay.
the warning.
You should have gathered town empty.
I was not sure if it was me, and I was like, okay, it's not me, it's just the time. Okay, so I feel better because I was like, maybe it's my presenting skills. Okay, so we're all good. Olivia, you wanna present? We have Inbar, right, first?
Yeah, so like I was saying, it seems that my sound connection is okay now.
Oh,
so
now,
I can try.
Cool.
And if it doesn't
we're missing Inbar as well, so I'm just going to ping her.
She was around.
Yeah, she was in the Gaverton, but let me ask her to connect to the Zoom.
Yeah. I think that went well, right?
Yeah, it was awesome. I need to chat about that poster, by the way, Flavian. So we can chat at the second poster session about the poster that because it was a bit too late when I arrived.
Sure. It's one easy trick to make your last click attribution.
Yes.
Causal.
I see that.
Exactly.
We try to get your slides ready. So I just pinged Inbar on the invited speaker chat. Boom, boom, boom. One minute.
So by
I
the way,
also
again,
noticed. I said,
ahead.
like, I just noticed that the latest statistics show like 1,024 attending the workshop. I like 1,024. It's a very nice number.
Take a screenshot. Take a screenshot. It won't last for long.
Yeah, exactly. Yes.
Hi, Inbar.
Regarding the panel, are we doing it? Inbar is here. Great.
Yeah. Can you try to just project your slides, Inbar, just to make sure that everything works fine?
Great. Can you still hear me, Yves?
Yep.
Okay, so should we start or wait a couple minutes?
Maybe let's wait maybe just 1 minute and start.
Yeah. Okay, sounds good.
Did anybody take a screenshot of the 1,024 attendees? That's very important. I'm serious.
I just did.
Okay, thank you, Maria.
We can always Photoshop.
It's really important. It's really important for us as organizers to make sure it's actually an evidence that it actually happened. Like not all of this was completely made up. Like yes, of course you've seen it. This is not the Truman Show. Inbar, can you try to speak? So if we can see.
Yeah, can you hear me now?
Yeah, great.
Okay, great.
Yeah, works perfect. So we're gonna get started in a few seconds.
Sure.
Again, we hope you enjoyed the Gather Town session. We welcome our next invited speaker, Inbar Naor, who is an algorithms team lead at Taboola. And Inbar is going to talk about challenges in evaluating exploration effectiveness in recommender systems. Thank you very much and welcome, Inbar.
Thank you. So that's actually like the first non-internal Zoom talk that I give. So it's a very interesting experience. I've been told that there are like 1,000 of you, but I'm just going to lie to myself and pretend that you're 12. So that's nice. Well, what I want to talk today about is exploration. And more specifically, I want to talk about challenges in evaluating exploration effectiveness in recommender systems. So I'm going to start by talking about what makes exploration uniquely challenging in recommender systems. And then I'll talk about the different ways to look at exploration and how we can use those different perspectives in order to develop evaluation methods. So unfortunately, there is no easy answer here. You're not going to get out of this talk with some sort of like simple recipe of how to measure exploration. But I hope to talk about the different challenges, where we can get inspiration from, and where I think we can focus in order to make advancement. So I try to make this talk as general as possible, but naturally a lot of the examples that I'm going to give will come from my experience. So just a few minutes about my settings. As I said, I work at Taboola. Taboola is a content and ads recommendation platform. So it means that we're integrated within different sites and we recommend different articles or ads or both depending on the settings. Like many systems, many recommendation systems, Taboola is a multi-stakeholder system. So that means that there are different stakeholders that we need to satisfy. First, we have publishers, then we have the advertisers, and we also have users that need to be satisfied. And my team is working specifically on new advertiser success. So it means that we're looking at the algorithms in Taboola from the point of view of a new advertiser that is entering the system. And naturally, it has a lot to do with the exploration. All right, so let's start by talking about what makes exploration uniquely challenging in a recommendation system. So for start, we're typically dealing with a huge action space or a huge state action space if we're in our settings and not Bandit settings. So it means that we have a lot of items, maybe millions of items. And if we also add context into account, then we have also like a lot of states, a lot of actions, and we have a huge space to explore, which makes it challenging. Another thing is that usually when we talk about our L, we make some sort of like stationarity assumption. However, the real world is not stationary. We have new items that are added to the system all the time. The state space is always changing. User changes their preferences. And finally, users and market dynamic adapt to changes. So it means that we're very far from the stationarity assumption that we sometimes make. And it also makes the problem of exploration and recommendation system a bit challenging. Another thing is that a lot of the time when we talk about regret or like about exploration, we talk about regret bounds. However, in practice, it's often not enough to bound regret. We might want to bound the probability of having some sort of like catastrophic failures for one of the stakeholder or for the entire system. And I'm going to talk about this specific point a bit more later on in the presentation.
Inbar, sorry to interrupt. A few people in the audience are asking if you could turn the presentation in full screen mode. Did you do that?
Even if in full, yeah, I'll try. I thought it is. Is it full screen now?
I think it's better. Can people?
What do you guys see?
Yes. Can people speak on the Zoom chats if it's better? Maddie, Chengling, much better? Better? Okay. Yes, you can go ahead. Thanks, Inbar.
All right. So let me try another thing. Maybe it will work better. Is that better now?
I think that's much better. Yes.
Okay.
Yes, great. You can go ahead. Thank you very much, Inbar.
All right. Sure. Okay. So usually when we talk about exploration recommendation system, we have some sort of like notions. We're dealing with sort of like cumulative regret bounds. So we're typically looking at some plot like this, and we measure the regret as the time horizon changes, or as the number of episodes, or the number of steps. However, again, in real world, it's not enough to measure the regret this way, because measuring regret in practice might be very hard. So for start, we don't know the reward of actions that we did not take, but that's usually the case. It's not something that is specific to a recommendation system. And also, as we mentioned, we can't assume stationarity in the reward or in the state dynamics. Now, another thing that is unique to multi-stakeholder system is that when we talk about regret, it's important for us to ask ourselves, regret to who, or the cost to who? So, for example, let's think about exploration in an ads display system. If I think about my system from the point of view of the system or the publisher that we're in, then I want to take into account the opportunity cost, which is how much the system missed by showing this ad and not something else. However, if I want to talk about, if I think about it from the advertiser point of view, then I might want to talk about the billing cost, which is how much the advertiser lost by showing his ads in this place and not in some other place. So there are different costs that we need to take into account, and combining those different costs, or even considering those different costs, make the notion of regret a bit challenging in multi-stakeholder system. The final point that I want to make is that it's hard to account for long-term effect. So for example, in ads display, my advertiser might churn, might leave the system if I don't explore good enough for the specific item of this advertiser. And that means that it's, and this is something that I usually don't take into account. So we're dealing with like very long-term effects, and it's not that easy to take this into account when we define regret. So what I want to argue is that in order to make advancement in exploration and in order to understand the effect of exploration in our system, we need to move beyond this like notion of regret, beyond this high-level view of what exploration is doing in our system. And I want to suggest different points of view to do so. So I'm going to start by talking briefly about each of those points of view. And then I want to talk about different ways we can use them in order to develop evaluation methods. All right. So the first point of view is the high-level system impact. That means, what does it even give us to have exploration in the system? It's not that different from the usual high-level perspective that we talk about in RL when we talk about exploration. However, the second and the third approach look at exploration from the point of view of like the items being explored. So if we think about it from this point of view, we can think about recommendations as a system that control a very scarce resource, which is the exposure of items to users. And exploration is only one of the tools that we have in order to give better chances to new items. So from this point of view, What we care about is the success of the target population, be it new items or new advertisers. And when we talk about success, we usually talk about it in terms of business KPI. So we assume that we have some sort of like business KPI that we try to optimize for as a company. And then we want to look at exploration from the point of view of the success of the target population. Another point of view which is related is fairness for new items. And in here, I talk about fairness from the point of view, again, of the new items and not from the point of view of like showing similar things to different demographics as people usually talk about when they talk about fairness and recommendation system. All right, so let's start. I want to start by talking about high-level system impact. So in here, what we try to ask ourselves is what is the overall effect of having exploration in our system? So when we think about it from this perspective, it's not that different from having those like regret bounds, but we might want to ask this specific question as well. What does it give us to have exploration? So I assume that we already have a main metric. Our goal here is not to define a new metric. We have a metric that we use to optimize the system for. For example, we can use user engagement. And there are many different things that you can do, and the experiment that you develop is very much related on your settings. So what I want to do here is just talk about one specific experiment as an example, and I encourage you to think about specific experiments for this question in your setting. All right, so this experiment was conducted by metr. She talked about it in her talk here, I think 2 years ago, about the YouTube recommendation system. And what they suggested is, first, let's compare traffic with or without exploration. So we fixed the model training, and we just compared traffic with or without exploration. You can think about it as trying to answer like the causal questions that Amit talked about, but in a way that the treatment here is having exploration in the system. So the problem with this setting is that it does not account for exploratory data available in training. So in order to account for that, which is obviously a lot of like the benefit of having exploration data, we do some sort of setting of parts. Can you mute whoever it is? I'm sorry. Thank you. So in order to answer the question of what does it give us to have exploratory data in the system, we can split the traffic to 3 parts. The first part will only serve exploitation data. Let's call it A. The second part is also exploitation data, but only 5% instead of 90%. And the third part, C, is displaying exploration data in 5%. And now what we can do is compare model trained based on A and B data to model that is trained based on A and C. So we have 2 models that are trained on the same amount of traffic, but one of them is using only exploitation data, and the other one is using a combination of exploitation and exploration data. All right, so that's just one experiment, as I said. I can't give a lot of more examples because they don't really have enough time, but the point of view is that we should stop and ask this question. All right, so the second part I want to talk about is the success of the target population. So here I think about exploration as something that tries to improve the performance of new items or advertisers. So my goal here is to define some sort of like short-term metric that is A/B testable and indicative of the long-term success. So Amit talked a lot about the relationship with establishing the causal relationship between the offline metric and the online one, but we also have the same challenge when we try to establish a causal relationship between the online metric and the long-term metric that we care about when we talk about success in terms of business KPI. So example to short-term metrics like that can be clicks, conversions, engagement, CTR, cost per action, you name it, it's really much depend on the settings. So once you have a metric, what you can do is some sort of like causal experiment in which you allocate some traffic to exploration. So some of the advertisers will get exploration traffic, and some of them won't get exploration traffic. And then we can use this data in order to establish some sort of like causal relationship in exploration, or to measure the effect of exploration. But when I talk about these settings, I sort of make like this implicit assumption that you have separate traffic for exploration. And when we talk about bandits, a lot of the time we talk about like one system that tries to balance between exploration and exploitation. However, in practice, in a lot of the situation, it's not really the case. In many situations in practice, you would find yourself wanting to have separate traffic for exploration. And the reason for that is that too much exploration can have a bad business effect. It can cost too much money. It can make the system confusing or unsatisfactory to the users. So in many real world applications, you might want to limit the exploration traffic, which means you will usually have separate traffic for exploration. All right, so let's go back to trying to establish a good, to trying to find a good metric. And when we talk about metric, it's important to remember like this sort of metric hierarchy. So on top of the ladder, we have business KPIs. Those are the things that we care about as a company. So when I talk about advertiser success, it could be like the percentage of advertisers that churn in the system. Then we have different long-term metrics. And then we have the online metrics for experimentations. Those are the metrics that you use in order to make decisions such as which exploration method is better in our system. We also have optimization metrics, and we have the offline metrics. Now, typically a lot of the talks in this workshop was dealing with the relationship between like offline and online metrics for experimentation. And rightfully so, because it's a very challenging problem that we really should address in order to make any advancement in the field. But in this specific topic, I wanted to focus on online metrics for experimentation and explore like the relationship between the business KPI, the long-term reward, and the online metric for experimentation. All right, so we want to define a metric. It's a good idea to ask ourselves, what do we even want from a metric? So the natural thing that we want is that we want the metric to be indicative of a long-term gain in the business KPI, because if that's not the situation, then we're just improving some sort of random metric that doesn't really affect what we care about. Another thing we want is the metric to be sensitive to changes and converge fast. So sensitive to changes means that if I do something that is good for new advertisers, for example, I want the metric to detect that. And we want it to converge fast and not to be too noisy, because this affects how fast we can run as an organization. If it takes our online metrics like a month to converge, then it means that each experiment that we have needs to run for at least a month, which is the reason that we don't work with the long-term business KPI to begin with. That's why we need proxies. Other things we might care about is we want the metric to be fast and cheap to compute and hard to game and incentivize the right action, but I'm not going to talk about that. So let's start by talking about indicative of the long-term gain in business KPI. One thing we could do is have some sort of like data set of past experiments that we know improved the long-term business KPI. And then we can look at the metric on the experiment itself and establish and see if there's a relationship there. But often we don't have this data set. So another thing we can do is look at the observational data instead of experimental one, and look for correlation between the short-term metric and the business KPI. So for example, if I think that the amount of clicks that a new advertiser got in the first week is a good proxy for the chances of this advertiser to churn, then I want to look for a correlation there. And another thing I can do is have some sort of classifier. So let's say I try to predict the churn probability based only on the number of clicks that the advertiser got in the first week. And then I can use the predictive power of this classifier in order to see how good a proxy it is. Now, obviously, the problem here is that all of those methods are talking about correlation, and what we really care about is causation. So causation is a big problem, and it's something that is qualified for a different separate talk or even like a separate workshop, honestly. And luckily, we had a talk about this specifically. So I want to say that a lot of the methods that Amit mentioned in his talk are also relevant in this case of establishing the relationship between the online and long-term KPI. But just like a quick example for another approach, so we should know that there's a lot of work in economics and statistics about experiments designed in order to estimate the long-term impact of the treatment. And when they talk about treatment, they usually talk about, when they talk like at the treatment impact, they usually talk about years or even decades. So there's definitely a lot of things that we can learn from there. And one approach is using surrogate. So a surrogate is a short-term proxy variable, and instead of looking at the outcome of our treatment on the long-term metric that we're interested in, we can look at the surrogate itself. But in order to do that, we need to make an assumption that the long-term outcome is independent of the treatment conditional on the surrogate. So this assumption is called the surrogacy assumption. So let's give a quick example. Let's say that I want to measure the effect of exploration on the future chances of an advertiser to churn. And I want to use the number of clicks in the first week as a proxy for that. So if I know that the probability of churn is independent of exploration method, conditional on the number of clicks, that means that any causal effect of the exploration method on churn is already reflected on the number of clicks, then what I can do is use this as a surrogate. And then if I assume some sort of like linear model, what I can do is like simply multiply the treatment effect of our exploration methods on the number of clicks by the regression coefficient for the effect of the number of clicks on the churn probability in the observational sample. All right, so that was very quick. I know, I'm sorry for that. I wish I had more time to talk about it, but I just want to talk about it briefly. And another problem that we have with these settings is that the surrogacy assumption is often violated. For example, if we go back to the clicks and the churn probability example, then naturally a lot of clicks don't tell the entire story. We also care about conversions. We also care about the cost of the conversions. So one way to solve this problem is using a surrogate index. So that means that instead of wanting the long-term outcome to be independent of the treatment conditional on one surrogate, we would want it to be conditionally independent of on a set of surrogates. And this gives you an advantage. If you think about it from like a causal perspective, then think about a causal graph that you have. Then it just means that you have more nodes to block the causal pathways between the treatment and the primary outcome that you care about. So that's like the advantage of having a surrogate index. All right, that was a very quick run through causality. But again, I'm just trying to give you like a taste of different fields that we can get inspiration from. So one last thing that we care about is sensitivity, but we want the metric to be sensitive to changes, but not too sensitive to noise. Again, we can use a data set of past experiment and see how the metric changes there. But we can also do some sort of the degradation test, because in a lot of situations, it's much easier to break something than to build something. So it might be much easier for me to do something that is harmful for new advertisers and then see if the metric detects this change or not. And obviously, another thing that you should do is run an AA test in order to determine the amount of noise and how much time it takes your metric to converge. All right. So that was it about the success of the target population and how we can do like this relationship between the long-term business KPI and the short-term metrics that we need in order to evaluate exploration. So the last thing that I want to talk about is fairness for new advertisers or fairness for new items. So from this perspective, it means that we think about exploration as a mean to improve fairness between new items and existing items. So what we do is there's different notions for fairness. One natural notion would be individual fairness, which means that we want similar individuals to get similar results. The problem here is that we assume that we have some sort of like similarity metric to work with. And that's not always the case. It's a challenging problem to determine good similarity between items or between the things that you care about in exploration. And also, even if you have similarity, the method to evaluate similarity might be biased itself. So instead, what we can do is talk about group fairness. And in group fairness, we assume that we have two groups, one with protected attribute and one with not. So protected attribute in classic fairness literature would be something like race or gender. But in our case, we can think about being new in the system as a protected attribute. And then we want the group with the protected attribute to get similar results to the group without a protected attribute. So again, what does it mean, similar results? There are many definitions. One definition is demographic parity. So it means that we want members of both groups to be predicted to belong to the positive class at the same rate. The problem with this notion is that it assumes that the two groups should be similar in terms of like the outcome. So let's think about being a new advertiser or an existing advertising. We don't really have any reason to assume that the group of existing advertisers should have the same probability of clicks as the group of new advertisers, because the existing advertisers are the ones that we already know succeeded in the system, while the new advertisers are combined of both good advertisers that are likely to succeed and advertisers that don't really have a chance to succeed because they either have very bad creatives or they don't have enough budget. So we don't expect those two groups to be similar. So instead, what we can do is talk about equalized odds, which means that we care about the true positive rate and separately the false positive rate, and we want them to be the same across groups. And if we only care about the positive outcome as an advantage, as we often do, then we can talk about equal opportunity, which is the same, but only focusing on the true positive rate. So those are all metrics for like classification, but they can also talk about metrics for scoring, like calibration or balance for positive class. So just one example for calibration, it means that if we look at all the examples that got specific score, we want them to have the same probability to belong to the positive class, regardless of group membership. All right, so all of those notions are very much related to thinking about recommendation system as point estimate. For example, CTR prediction. And I think it's a good time to stop and talk about like the different formalization for recommendation system, because the way we formalize our system very much related to the metric that we can use. So for example, if we have a CTR prediction problem, if we treat a recommendation as a CTR prediction problem, and we have some sort of like mechanism of action, or we multiply the estimated CTR by the amount of money that the advertiser is willing to pay before we do ranking, then we can use those metrics pretty much as is. But in many situations, that's not really the case. By the way, that's also might be true for Q-learning. But if we talk about ranking, if we talk about policy learning, or any sort of reinforcement learning or Bandit settings, then we need to make some modifications, and we need to be aware of certain things in order to use fairness metrics for those problems. So I'll start by a couple of minutes about RL, then a couple of minutes about ranking, and then we're done. All right, so a couple of minutes about fairness in reinforcement learning. One problem with using fairness metric, as I described earlier in reinforcement learning, is that they don't consider the effect of short-term action or long-term rewards. So there's a really nice paper that got the best paper in ICML in 2018 that showed that applying fairness constraints, like the ones that I presented earlier, may cause more harm to the group that you try to protect, even at next iteration. So what they did is that they trained a model based on some sort of, or based on different fairness criteria. And then they used the data of this model to train a new model. And they showed that already at this next iteration, in some situations, you might have caused more damage if you use the fairness constraint than if you didn't use it at all. So the message here is not that we can't use fairness metric if we're dealing with the RL. Their message was mainly that you have different metrics, and based on based on the different scenarios that you have, you need to choose different metric in order to make sure that you don't cause more harm. So we need to be very mindful when we choose the action and see how they affect the long-term outcome of the actions that we make. But another option is saying, okay, why should we even talk about short-term metrics? Let's talk about long-term reward. Let's formalize fairness in reinforcement learning as wanting that the probability of choosing an action with lower short-term reward will be not very high compared to a different action that have higher long-term reward. So we kind of avoided this short-term reward problem by using the long-term formalization. However, there's a different paper that showed that if you use this kind of notion and you use fairness constraint based on this notion, then it might take you exponential time in the number of states to converge to the optimal policy. So there's a price to using this formalization. All right, so there's a lot of work in this field, and I think that it's a very interesting direction that we should think about when we talk about exploration in general. The last thing I wanted to talk about is fairness in ranking. So if we think about recommendation system as a ranking problem, then the problem here with using like the regular fairness metric is that small changes in relevancy can lead to large changes in exposure. So you wouldn't detect it in the metric, in the fairness metric, but then the outcome would have a very significant change. And also the other way around is true. It doesn't matter if the model predicted 0.4 or 0.6 if it doesn't impact the ranking. And this is something that would change the fairness metric a lot, but it doesn't change the outcome itself. So we don't really care about it. Okay, so there's a lot of work in this field, actually. There's a lot of work on adapting fairness constraint to fairness metrics to ranking. I just put here some references for you to use. And I'm not going to get into it because I only have like half a minute left. So to summarize, I talked about the unique challenges of exploration in recommendation system. And I talked about the fact that, well, okay, my opinion is that we should go beyond the usual reward maximization perspective in order to make advancement in exploration. We need to look at exploration mechanism from different points of view. And I suggested 3 different points of view for exploration. The first one is maximizing the overall utility, which is very much similar to what we usually do. And the main challenge here is conducting the right experiment. Second is that we should think about exploration as improving the chances of new items to succeed in the system. And the third point of view is the fairness perspective. So that's it. I'm not sure I'll have enough time for questions. So in case I don't, that's my email. Feel free to write me, and I'm also going to be in the next poster session. So find me in this application. Thank you.
All right. Can you hear me, Ingvar?
Yes.
Yeah. Okay, cool. Thank you very much. Indeed, we have very little time for questions, but one of the questions we got in the chat was, could you please elaborate more on the fairness in ranking if we have time?
Yeah, okay. So actually, I don't see how we'll have enough time to talk about.
Yeah. So I think that's a question. I think that's a question you could take in the poster session.
Yeah, that's a good question. Let's talk about it in the poster session.
Yeah, and one of the other question we had was complex ML models may be more accurate.
Sorry, you broke.
Yeah, I think Olivier broke up. Maya, that was your question. Do you want to ask the question directly?
Yes. So the question was complex ML systems tend to be more accurate at exploitation time, but at the same time, they need a lot more data to be trained, so they require more exploration, whereas simpler models may be less accurate, but do not incur such a large exploration cost. So I wonder how you think about this Pareto front.
That's a good question. Well, I think like it's like the usual dilemma of having like a more complex model than having like a simpler model. And I think it's actually doesn't really, it's not much different than evaluating any exploration method that you try to achieve. I think the way you would approach it is using the same tools, and the way to like balance between the effectiveness of exploration and the accuracy of the model, it's really much depends on your settings and how important it is for you to have like an accurate model versus like efficient in exploration or something like that. So if you have like a CTR prediction problem, then and you do auctions, then maybe you are okay with like neglecting some items and neglecting some things that you can explore in order to have more accurate model. But if you're in different settings, then maybe accuracy is not that important to you and you need to focus more on exploration.
Thank you, Inbar.
Thanks.
Thank you. And now, panel.
Indeed. And thanks again, Inbar. That was absolutely amazing.
Thank you, Inbar. Thank you very much.
So the way we think to proceed is to actually ask people from the audience to ask us questions in the session Q&A. And then we will pick them up from there, and then we will discuss them. So let's see what people come up with.
And just to be clear, so the Q&A is the Q&A that's associated with the panel session in Whova. So you need to go to the next item in the agenda in Whova to see that.
I posted it in the Zoom chat too, just in case. I think it's the right one. Okay, we have a first question. How would you incorporate safe exploration in certain application? Exploration has certain risks. Very good question. Who wants to take it? Inbar?
So I wasn't here to hear the question.
No problem, I can repeat it. So how would you incorporate safe exploration in certain application? Exploration has certain risks.
Yeah, that's a very good question.
Like all real applications.
Yeah. Well, I think there's like, if we look like farther into the future, we would want to have like different constraint-based optimization in exploration as well. But I think it's going to take some time to get there in like a effective way. And well, I'm very biased as a practitioner. So the practitioner answer for that would be to have some sort of like different traffic for exploration. To bound it, you can have different business rules, in order to bound the specific thing that you care about. So if there's different outcome that I'm very afraid of, then I can bound this outcome with different filtering or different business rules in my production system. So I know it's like not a very practical solution to a very challenging and interesting theoretical question, but I think that's what we should do until we reach a good solution from the theoretical perspective.
A quick follow-up, Inbar. So do you think it would incur any form of bias in your system if you start putting a bunch of heuristics? Yeah.
Yeah, most definitely. I think one way to address it is using like the same tools of like of policy evaluation methods. So if you also have like random traffic data, you can maybe use that in order to correct and evaluate for some of this bias bias. But obviously, yeah, it's a very good point that we need to be mindful that every business rule that we introduce in the system will introduce bias that we need to take into account.
If I could like pitch in for a second, what I guess it's gonna be a bit kind of self-serving. I'm gonna mention some of our recent work that we did with Bayesian organic models for Bandit feedback. I think it's very important to use, in some sense, informative priors. So especially in recommendations or in large-scale recommendation, where we have a lot more actions than we can actually explore. So we'll always have to concentrate on a couple of good candidates. I think you have to have kind of a modeling approach to new actions or to new items. You have to have some form of goodness score such that you can try things that are likely to succeed online. I think without it, you will just be drowned, and especially also if you have a small causal effects. Just waiting and exploring until you find how good this new arm is. It's just you might just not have time to do it. So I think you'll have to somehow get some form of prior information from some other source to be able to do successfully some exploration. I think we have other questions. I think maybe we should move to the next one.
Yep, let's do that. So what I'm particularly curious about is the question from Adif on do we anticipate new fairness constructs and metrics and concepts as we deploy reinforcement learning for recommendations, e.g. ensuring that a subset of early adopter users don't keep getting targeted as exploration traffic? And I wonder, Adif, are you on the call? I would be super curious to hear your own take about that as well.
I am on the call, but I'd love to hear answers. I also saw there was an interesting position paper out of MSR Montreal that brought up a lot of fairness issues as they anticipated more RL being deployed, but no concrete proposals for how we might actually encode them into some constructs that we can study. So I'm actually very curious to hear from the panel.
Because Maria, do you have any thoughts on that regard?
Yeah, I think that the fairness constraints, when we employ them in RL, we need to make sure that they look into the long-term reward we try to optimize, because as Invar mentioned, it gets easy to have a fairness constraint on a short-term metric, but then gets misaligned on the long-term metric. So that's definitely something that I would keep in mind.
So I guess no easy answers.
I'm actually also curious if people have tried the existing fairness notions in these interaction systems and seen failure modes for like, where does it seem to come short?
Yeah, I can give one example from our experience. Yeah. So we tried multiple like classical fairness metrics. And the place that it's not really aligned with what we try to achieve in exploration is that when we think about accuracy of the model, and a lot of the metrics are essentially talking about some different notions of accuracy, then we sort of make this implicit assumption that having higher accuracy is always good. And in exploration, in a recommendation system, it's not always the case. Some items can benefit from like lower accuracy, but to their advantages. We need to remember that error goes both ways. So we might be in a situation in which we improve the accuracy of the model, but we actually hurt the items because before that they had some sort of error that made the model more optimistic towards them.
That's fascinating. Yeah. And in retrospect, it seems obvious, but yeah, that's fascinating.
If I may follow up on that, particularly on the example you provided that is on early adopters not being targeted as exploration traffic, there is clearly a trade-off. For one point, like an early adopter, you want them to have kind of a good experience because they're a new member, and you want them to help them benefit from the service. So maybe exploitation helps under that assumption, but at the same time, there was one of the RecSys papers that pointed out that more exploration and basically exploration on the recommendations can increase the diversity of what these new users experience. So we may not want to tune down a lot the exploration for these new members because we may be able to benefit them more by having them explore more so that they can be exposed to a more diverse set at the beginning. So definitely, I don't think there is one size fits all. One could think that reducing exploration for new members might provide better experience, where in fact it reduces that user the diversity, and it can lead to worse experience in the end, particularly because we don't have much information for them yet.
Another quick fact on that as well is that so there's been quite a few proposed fairness metrics in recommender systems looking at fairness in exposure. So trying to understand whether the exposure itself, so the recommendations that you provide are fair. But it's really interesting to try and extend this concept to sequences of exposures as well. Right now, all of them are defined as point-wise metrics, but it would be interesting to see what it looks like in a sequential context as well. So we might need to think about adapting some of these fairness metrics to the reinforcement learning setup. I wonder whether, Flavian, we should move on to the next question as well. There's one in particular that I think would be super relevant for you to answer, Flavian, on what's your attitude towards evaluating recommender algorithms in simulation, and how has it changed recently, if at all?
This was, I had actually this one as a backup question for us anyway. I don't know, actually. This is why actually it's a very good question. How do you find what is the best simulator out there? It is I think what like my beginning of an answer to this, I think is kind of, we need to characterize a bit what the simulators are assuming about the environment and about the type of the Bandit feedback, what's the sparsity, what's the stochasticity, what's the signal to noise ratio, all of these things. I think there are different regimes. Like if you're trying to, for example, simulate some form of an advertising scenario, as opposed to, let's say, a recommender system like in YouTube, I think the causal uplift in these two scenarios might be totally different, right? So it's probably, some methods might work in one of the regimes and some methods might work in a different regime, right? So I think as long as we know what the simulators simulate, like kind of what kind of data regimes and signal regimes they are about, I think basically they're all kind of good in their own. And of course, if a model can perform in multiple simulators better, it's more robust, therefore it's more general, like we do with the data set. But it is true that it's quite hard, and it's something that we also are trying to see how to benchmark against other simulators, or how to compare simulators as they start popping up more and more.
Yeah, and actually on that note, so there's a follow-up question by Andrea on how do we evaluate the quality of simulators, and so are there any metrics that we can use to compare simulation environments?
Yeah. Tough. I would say ease of use, adoption also in some sense, kind of opportunistic, right? Because the more a simulator is adopted, then you can refer to other prior work. So that there is always this, which is not necessarily satisfying. And then in some sense, again, how close to reality they are. And then that's the question then again is like, what is your reality? For example, when we design Record Gym, we really thought about the advertising use case. So for us, it's really close to what we know advertising to look like. It returns reasonable, rates, CTR rates, conversion rates, uplift deltas. But again, it's not a tool that can be used generally with the same hyperparameters, of course, it could be retuned. And then you could think about basically different configs or different environments on which you could say, so I would say to look at the simulators as being, as we do for RL, as being interesting, challenging, how hard they are. I think if, for example, if you want something like a full RL, you will have to look to see if these simulators are actually doing full RL simulations. RecOGym just added that functionality. So I think it's an ongoing list of things that needs to be checked. Yeah, I'll have to think more to be able to give a very good answer to this. But yeah, it's something that we'll have to start comparing, because there are many simulators showing up. And now there is also this new work with the offline data set, which looks very promising. I will take a look and I had actually a question for the others, which is, at least for the data sets, what we had when we did the counterfactual data set at Criterion, the problem that we had is variance. It was very hard to evaluate any policy that was a bit different than the logging policy, right? How much exploration basically, because they had a uniform collection policy. I think probably they have pretty good coverage, and probably you can use quite a lot of policies and you can still conclude. But this is when we decided to do a simulator, is when we saw the limitation of a Bandit data set, even with propensities. We wanted to really be able to simulate any policy as far as we want from the logging policy. So I think that's in general a good thing about the simulators, but then again, how do you compare between them? That's a tough one.
Goes with caveats, indeed. Yeah. And I guess the variance issue becomes even worse as you start trying to evaluate reinforcement learning algorithms as opposed to Bandit algorithms as well. It's
right.
Yeah.
And
so you need something like that.
The risk is always to create a simulator for the algorithm, and then basically every paper.
Which is kind of the case already, but yeah.
As a reviewer, it's very hard to say, why don't you use my simulator? There is already one. But I do think we should at least try to use each other's simulators as a kind of first step.
Yeah.
And then, yeah, maybe just get in the practice of using multiple simulators when publishing on this. I think that could be good.
Maria, did you want to jump in?
Yeah, a quick follow-up on that. Something that Justin Basilico had in his Netflix Expo talk, and I really like, says that if you have like a pretty good simulator, it means that you already have a pretty good recommender system. So I would definitely underscore the need of looking at an ensemble of simulators and what different policies can you derive from this ensemble of simulators. And in terms of comparing simulators head to head, if one has access to A/B testing, I would consider like policies that the different policies that come out of the different simulators to be compared in an A/B test. That would be an interesting comparison, and it would be tailored on the particular use case that one has.
Right. Good point. Should we do one more?
Yeah, there's a ton of other questions, so it's hard to select which one.
Well.
So one that is interesting is that naturally some people like to explore new stuff. So some people are more keen on exploration. And what are your thoughts on personalized exploration and trying to potentially use that property?
Oh.
Inba or Olivier, I'm curious whether you have any thoughts on that.
I know I seem like a natural candidate to this answer, but Tabula's setting is that we have probably like the least knowledge about the users than any of the other panel members, because we only rely on cookies. So for us specifically, it's not very practical to use this fact, because people, they change cookies all the time. So it means that I have no experience with it whatsoever.
Sounds good.
Yeah.
Cookies are annoying.
I don't know if you can hear me. Can you hear me?
Yes. Yeah.
I would tend to think that I wouldn't cluster people between those who like to explore and others, but maybe more, I think we all have different personas, and there are different situations where we are in exploration mood and less in an exploration mood. And I think that's probably one of the area where it's definitely the case is movies, right? So I would transfer the question to you also, Eve, about Netflix, but I'm pretty sure that there are situations where you're definitely not in an exploration movie.
True.
Right, so we lost Olivier on the...
Yeah.
Sorry,
that's
Hilda?
me.
So one thing that we did try, which is like along this line, is like related to what Olivier said, is that instead of thinking of users that are in exploratory mood or not, we thought about whether users are clickers or not, or whether they are more likely to converge in general. And then we compared the different users that a new advertiser got versus existing ones, or like the different user that you get in your exploration mode. And I think that's also an interesting information to take into account, because not all exploration places are equal. You might be explored to a user that would never click on an ad, and then we didn't really give you a fair chance. We only think that we did. So that's also something that we're trying to take into account.
Sounds good.
I have maybe like a different take on the question. So I always think of exploration as trying to gather information about the user's preferences. And I interpret the question as saying that the user's underlying preferences may be quite diffuse, as opposed to, I mean, in certain contexts, I could have a much more broader set of interests that I would consider as interesting recommendations. Whereas in other situations, I really don't want to be bothered by something outside of a very narrow preference. Like right now, I am trying to find a specific item. Don't bother me with like 20 irrelevant ones. And I haven't yet wrapped my head around this concept of a personalized recommendation. I find it easier to separate between the user's underlying preferences, and exploration is purely a tool to give me signal on what that could be. And it could well be that the user's underlying preferences may be more or less diffuse in different contexts.
That makes sense. Thanks, Adif.
I guess one idea here that I just popped into my head, and maybe that could be actually future research, is like to think of recommendation actually as new preference forming. So actually you're not trying to discover preferences that already exist, but you're actually, so you basically increase the latent vector in some sense, right? So then you develop a new taste that was not even there.
That's interesting. I remember our conversation with Adif last year on exactly that. I think that's a very interesting framing.
And Minmin's group has work on this, right? Like I think either Craig Boutilier's team or Etchi's team at Google had a sequence of papers on nudging user preferences in
interesting.
Like the chocolate kale model.
So maybe we'll hear more about that later today. One very quick question before we wrap up and move on to the next invited talk is a question from Arnie on how to deal with massive item spaces where, even propensity-based method might completely blow up even with randomization. So one quick plug there would be, so at the Reveal workshop last year, we presented a paper called Recap, which is a very simple off-policy evaluation that helps with basically this type of problems by basically incorporating some soft matching aspect as well. Another one that may be useful to investigate is doubly robust techniques as well to try and make use of the full data as well. So that there might be a bunch of different options, but if you have generally very sparse feedback across and there's a very long tail there, it's always going to be pretty high variance. So.
The blob model, very important.
And the blob model, yeah.
Use prior information on the similarity between items.
Yes, yeah. So basically looking at co-occurrences and trying to use that as prior as well. So yeah, there's a bunch of techniques, but most of them are pretty new. All right, I think we should probably start getting set up for the next talk. What do you think, Flavien?
Oh yeah, I think we should. I think Hussam is right here.
Sounds good.
Hussam, are you ready? Can you hear us?
Yes, I am here.
Okay, great. So it's my pleasure to introduce Hussam Nassif, who's a senior machine learning scientist at Amazon. He established and leads Amazon's adaptive testing framework team. His main focus is on researching and deploying in practice Bandit and reinforcement learning algos. And he's also interested in causality and diversity. So he's one of us. He helped launch more than 20 live products while he stayed at Amazon, Google, and Cisco. And his research work has been recognized with 4 paper awards, including the ones at RecSys 2016 and KDD in 2017. And today he's going to talk to us about solving inverse reinforcement learning, bootstrapping bandits, and adaptive recommendation. So, Sam, you have the honor.
Thank you, Flavian. I really appreciate the opportunity. Let me share my screen. Okay, everybody sees my slides?
Yep.
Awesome. Okay, perfect. So today I'll be presenting 3 distinct RL and Bandit projects, and that have 2 qualities in common. The first is that they all leverage reward signals to inform recommendation, which is the gist of this workshop. The second is they all were led by interns, and that's a point that I'm really proud of.
It's a good feature.
Exactly. And so, so the first project, Solving Inverse Reinforcement Learning, is led by Sinang and was published at ICML 2020. So solving reinforcement learning is a big claim. Let me explain. First, let us remember what inverse RL is. The aim is to recover a hidden reward function from observed agent demonstrations. So a common example that people use, and I plug this from a source from Shimosuke et al., is that it's autonomous driving. So you have a car, you record drivers driving the car, you have all these data, you apply RL to uncover the driver's decision process, and then you use and apply it on novel scenes, right? So that's one of the classic examples of inverse RL. So here's a reward function. Recovering the reward is not easy as it seems. Given a reward function, an agent follows a policy and generates demonstrations. Based on these demonstrations, RL attempts to reverse engineer the reward. The difficulty lies in the fact that different reward functions could explain the observed demonstration, making it impossible to identify the true underlying reward function. This is called the identification issue. And this is a real issue in IRL. The way that we solve this identification issue is that we add a concept called an anchor action. An anchor action is the assumption that each state has an action whose reward is known a priori. This is a key assumption. You may object, hey, it's a very restrictive assumption. How can I really have actions with known rewards in advance? Well, it turns out this assumption is often naturally satisfied. It could simply be the action of doing nothing with 0 reward. Given this reward function, and here notice, it's important to notice that we are allowing the reward to depend on both state and action. As other restrictive RL methods only assume a dependency on the state. And so the reward function and the agent executes a policy, well-observed demonstrations, and we can prove that using our PQR method, that's why I'm explaining in a second, we are able to correctly identify the exact R, the exact reward function that generated the observed demonstrations. Now, one thing to keep in mind is that RL assumes that demonstrations result from an optimal policy. But it's impractical to assume agents always make the best choice. We remedy that by assuming agents maximize and follow energy-based modeling. What does that mean? Under this paradigm, the optimal policy itself is stochastic, and you can see it, it's a softmax. So energy-based modeling really allows us to express and model randomness in an agent's behavior, and is much more realistic. Also, it's important to note that most other methods require a deterministic optimal policy. So that's an advantage of our method. If you really care about deterministic policies, then you can simply set the alpha to 0, and then you get a deterministic policy. So how does our method operate? We call our method PQR. P stands for policy, Q for Q function, R for reward. And the reason we call it PQR is because it is sequential. And so we first estimate the policy, we then estimate the Q function, and finally we estimate the reward. The first step is to estimate the policy. And for that, you use any stochastic policy estimator for energy distribution. Pick any of the shelf estimator, just get a policy based on your demonstrations. The second step is the Q function estimation. And here we run into identification issues, as a wrong Q function induces a wrong reward. This phenomena is called shaping. And so this is where we leverage our anchor action. This is where we leverage our anchor action assumption. And we use it to solve a fixed point contraction to uniquely estimate the Q function for the anchor action. It's basically a one action MDP. So that's easy to solve. In practice, though, we do not know the transitions. And so what we do is that we use a fitted Q iteration to represent our Q function. What is a fitted Q iteration? It is basically where we use a deep Q network strategy on which we apply the contraction repeatedly over the demonstrations. So the sampling comes from the demonstrations, and we apply a contraction over a Q deep network, a deep Q network. Now we have estimates of the policy and of the Q function for the anchor. Well, it turns out that these are sufficient to identify the Q function for all state action pairs. Now to the final step. We have a policy estimate, we have a Q function estimate. We are able to estimate the reward using supervised learning. And you can see the final equation down there. And so you can see that the final equation for the reward only depends on Q and on the policy pi. We have an expectation, and that's the expectation where we need the supervised learning. And to be able basically to use the demonstrations and get the expectation out of them. And so once you thread PQR together, you are guaranteed to recover the actual reward function. And this is something we prove in the paper. So we have various theoretical guarantees that comes with it. The most important is that we prove a non-asymptotic upper bound on the estimation error of PQR. It's under a bunch of assumptions. Check the paper to see them. And again, the major assumption is the existence of anchor functions. Now, this method is pretty competitive. And so here are some results. And we are plotting the mean square error MSE. So lower is better. And as you can see, the PQR, like it barely registers on these histograms. Now, as you move to the right, the problem becomes harder and harder. It's basically the state feature dimension increases. And you can see that basically, even with larger state feature dimensions, PQR is pretty close to 0 in terms of MSE. So that's very promising. That concludes the first project. The second project is about bootstrapping bandits. And it was led by Sori, and it's currently under review, but you can see the archive version. Here's a toy example. So let's say you have an ad, and this ad has multiple slots. Now, for each slot, you have multiple alternatives per slot, right? So it's a combinatorial setting. And you want to figure out which one of these combinatorial ads is the best to show customers. Now, our representation captures all pairwise interactions as second order features, right? So we basically take any interaction, title and image, button and text, and so on and so forth, and we featureize accordingly. You can featureize in different ways, but I'm at least using a simple example to show a point further. So here's how you fit your first order features. So these are the variant values, image 1, title 2. You have your second order features. These are the combination and interaction between the features, something like image 1 and title 2. And finally, we concatenate them to form our final feature vector. Simple concatenation. we feed all of this into a Bayesian generalized linear model, right? There, because it's Bayesian, each feature is associated with a distribution. And then you can see where this is going, right? So basically that's your contextual bandit. That's your generalized linear model bandit, right? And usually these bandits, like, because it's a Bayesian system, any Bayesian system has to start from a particular prior. And so typically here, what we do is that we use some non-informative prior, typically N01, standard normal, right? Your standard Gaussian, but it could be whatever you want to use, right? Some non-informative starting prior. And so the question that we wanted to investigate in this work was, hey, am I able to leverage the data to start from an informative prior instead, as opposed to the non-informative prior that we start with? Remember that our features can be divided into two categories. In my toy example, it's first order category and second order category, but it could be anything, right? Absolutely any feature grouping that you want. You can have like customer features in one category, content features in the other, or local versus global features, whatever you want. Right? Some categorization. And then what we do is that we impose a hierarchical meta prior on these categories. So basically I say, listen, instead of starting from a non-informative prior, I want each category to start from its own informative prior. And where do I get the information for that informative prior? Where I compute it empirically from the data. Here's how it works. So this is basically our empirical Bayes algorithms. First, we start with a non-informative prior. So this is your standard Bandit starting from scratch. Nothing fancy. You run your Bandit for some time. So you gather initial data. Let's say we run it for 1 day, right? And typically, like usually your first day is the Bandit operating completely random, but it doesn't have to. Like even if you have some policy or you run it for multiple days or you update, this is totally fine, right? The method still works. But the idea here is that you run it for a limited amount of time and you gather a limited amount of data. Then we bootstrap this data. So we take this data and we use this data to compute empirically, in hindsight, a good prior, right? So I'm using this data twice, right? And so once I compute in hindsight a good prior that helps explain this data, then I can restart my model. But now, instead of restarting with a non-informative prior, I start with an informative prior coming from the data. But now, remember that I had run this model for 3 days, let's say, or 2 days, or whatever, to get the initial data, right? Are you telling me that I should throw away this whatever I learned, right, just to compute the prior? The answer is no. This data you didn't throw away. You can reuse this data to rerun your model and bring it up to speed to the 3rd day, right? So basically, we use this data twice. Once to compute the empirical Bayes priors, second time to run the model for documentation purposes. And now your model is back up to speed, right? It's on the 3rd day as if nothing happened, right? And then you simply continue using your model for documentation and run as usual. Like put it into production, run it for 2 weeks, however long you want to run it or you want to do it. So that is the basic idea. I'm abstracting a lot of mathematical details similar to what I did with the first project. Please check the papers for all the maths involved in this computation and how exactly we compute the empirical priors. And so here are some results. So here, lower is better. That's your log loss. The question that we asked is, if I train at day 1, or at day 2, or at day 3, right? How is this affecting my performance? And basically, we can see that the longer you wait, the better. But at some point, like it's a trade-off, right? But here we plotted 3 different days. So the first one is you don't do the empirical Bayes idea, right? You just run your Bandit as usual. The blue is where you do it after the first batch. The green is when you do it after the 3rd batch. And you can see that first is better than 0 and 3rd is better than 1. So lower is better. And the more you wait, the better it becomes. The second one is, well, how well do we do this, right? Like what's a good judgment for that? So this is a live experiment. The y-axis is my success rate. Because it's a live experiment, I can't plot regret, right? So I have to plot success rates. Here, higher is better. And we can see that the empirical-based Bandit converges faster, like a couple of days faster, right? And it's more stable. Now note that all of these prior or meta-prior, like in the empirical-based methods, they will not eventually change your result. Like if you have a lot of data, data trumps prior, right? But if you have scarcity in your data, if something takes too long to converge, then basically bootstrapping your Bandit in this manner, where you are able to use your data twice for empirical purposes, then basically it allows you to shave a couple of days off, which could be a determinantal improvement. Perfect. So the final project that I'm presenting today was led by Ari, and it was published at KDD last year. Adaptive recommendation is the gist of this project. And by the way, like these are not the titles of the papers, but this is the main point that I want to put in this particular workshop. And for all of these papers, if you click on the links, you could actually go to the paper, and they're all on my website, and I'll be uploading these slides too. So suppose you want to search for an item, but you have no idea how to describe that item, right? So Jackie Chan is really frustrated. He has no idea how to describe this pointy white star. But if I give you two choices, you can tell me which one is closer to your target item. The target item is hidden from me, right? If I'm the system and you're the user, I do not know what's in your head. You know it, but I can basically show you a bunch of I can show you a bunch of items, and I rely on you to tell me which one is closer to your target item in your head, right? And so basically you look at these and say, you know what? Probably the white one is closer because they share the same color. And so what just happened in here? Basically, in your feature space, right, in your head, you realize that the distance between the white sphere and the star is shorter than the distance between the black sphere and the star, right? We can even mathematically represent the probability of a user picking item A or over item B given the target. This is cool, right? Why is this cool? So this is called the triplet in machine learning. Because if I observe a bunch of preference pairs, if basically I show you a bunch of these two pairs and you tell me which one is closer to your target, then basically I am able to compute the likelihood of your target, the likelihood of the star. And then I can sample from it. How is this useful? Here's a toy adaptive real-time search application. Say our feature space has two dimensions, right? Pointiness and color gradient. And we need to interactively find the target in the user's mind. So this has to be in real time, right? And so here are the items that I have in my catalog. And the target item that's hidden from me is the white star in the top right section of your screen, right? It has the red arrow. The system presents two options. The user picks the closest to the target item, right? The system recomputes the likelihoods. And so as you can see, it's grades. It's not eliminated because basically the likelihood mass shifted away from the grade part of the screen. But it's always there. I potentially could resample it, right? And so the system recomputes the likelihood and then shows two other options. And then it repeats. I pick one and it repeats, right? Now it's showing me closer options to my target, right? I pick one, and then finally the system is able to identify the actual target that I had in my head. Now, in reality, we show a slate of recommendation and apply this algorithm in embedded space, but I'm not going into these details. Again, you can check our paper for more complex use cases. So what happened in here? The first one is that our representation allows for a fast pointwise target estimation. I can very quickly, in linear time, compute all the target likelihoods for all in my catalog. Very large catalog of items. And I haven't solved yet how to decide on which item to show the user in order for the user to express likes and dislikes, right? And so I need a fast real-time contextual bandit. And at these large scales, contextual bandits tend to be slow. So what can we do? So we generate a discrete distribution using a softmax equation. And then we perform fast sampling using a Gumbel softmax trick. And finally, because the Gumbel softmax trick and your standard Boltzmann bandit lacks an uncertainty estimate, we add the uncertainty estimate through annealing. And we get this function. What did I just say, right? How can I, what does these 3 points mean? Here's what it means. G is the likelihood of star. It's the likelihood of your target. That's your pointwise estimate. And that we can estimate really quickly, right? But whenever we estimate it, it does not come with confidence intervals. So I need to add uncertainty somehow into my bandit. And J is the number of interactions that the user has done with item J. So basically, this is the annealing part, and this is how I am able to inject uncertainty based on exploit into my system. That's the Gumbel softmax trick. It's basically a very easy way to sample once and be able to compute a maximum over exploit. And the reason is that, like, once you take these three together, you are recovering your softmax distribution. And so now you have a very fast way to sample, because softmax is very efficient, right? We are able to use this as a posterior to pick the items to show you. And essentially what I got is that I got a contextual Thompson sampling bandit behavior using fast, non-Bayesian, and non-contextual techniques, right? So it's a poor man version of that that's pretty efficient. Here are some results. And so our Boltzmann softmax bandit, that's what we call it. And so here, lower is better. So this plot shows the number of time steps that are needed till the user finds the target item. Lower is better, and you can see that our solution outperforms the other solution. In this graph, higher is better. And again, you can see that our solution outperforms the other solutions. And that's the recall of our method, right? And with that, I want to end my presentation. I'm open for questions and comments, and I want to point you to the papers themselves that you can find on my website. Thank you.
Thank you so much, Sam. This was an amazing presentation. So many good ideas. And now let's go to the Q&A. I think we have a couple of them. So let's start with the first one. So the first question is: PQR robust in situations where demonstrators use a different state representation than what the policy uses? I'm worried about the causal confusion in imitation effect.
That's a great question. The short answer is that no, it's not. If basically you pick the wrong action, even if you pick the wrong anchor action, PQR is not robust anymore, right? Now, what you can do again is that you can simply say, okay, I want to pick the no-op action and then apply to it a reward of 0. And if you do that, then we find that basically it behaves okay. But the anchor action is a really limiting factor.
Important. Right. Okay. For the second question, in the URL setting, you suggest, I am not sure I understand which users are agents in the imitation reinforcement learning.
Oh, yeah. It's basically whoever generated the demonstration, right? So in this particular example here, it's the driver of the car that you recorded in order to extract the reward function.
Okay. So before I ask a question from the audience, since I'm here, like a personal question, do you believe this can be used in recommendation to really reverse engineer the user preference functions?
Well, so if you check the paper, we do also apply it to real data sets, right? Now, the real hard thing is that often the reward function actually is hidden from you, right? And so it's really hard to answer this question because you don't know what it is. So in simulations, we were actually able to uncover it. And then in real-time data sets, so we actually took an airline data, and we tried to reverse engineer the airline's decision and figure out when to open a particular airline route between, right? But we can obviously not go and ask them, hey, what was your reward action? And so we measured, okay, how much error did we do? Could we predict what's the next route that they're going to open, and so on and so forth. And we found that we had decent results, right? And you can also check the paper for that. We converted to other methods on this airline data set, and we outperformed all other methods. But can I always be certain that that reward function is the actual reward function that somebody used outside of a simulation perspective? It's hard. It's hard to know. Okay,
interesting. But yeah, I would be really interested to see if we could use it in a recommendation setup, or if you tried it. But I guess, yeah, I'll have to pick up some more questions from the audience. So the next one, there is a lot of emphasis on the first day's data when it is used both for the empirical prior and the posterior. How is the method robust to rapid covariate shift, early versus late adapters?
Good question, right?
So this is, I guess, for the
yes, yeah, exactly. And so here I want to show two things. So, oh no, I don't have that plot here. Sorry. In the paper, right, we do some robustness analysis, and we also try to say, okay, because I'm using the data twice, or at least that initial data twice, right? Can I let the Bandit itself use it twice and see what happens, right? And we see that no, like even if you feed the data twice to the Bandit, the performance is going to decline for the Bandit because of overfitting, right? While for us, because we used it simply as a prior, and then later data is going to trump my prior, we are able to adjust better for such adverse situations.
Interesting.
Yeah.
Okay, and the last question we have, for adaptive recommendation setting, are session-based metrics better to measure than single impression metrics?
Can you repeat the question?
For adaptive recommendation setting, are session-based metrics better to measure than single impression metrics?
Oh, yes. Yeah. So basically this. So here what I show. The important part in here is that you are able to do all of this, right, in real time. So this is one session. The user comes. The user has to search for that star in real time. So all of this has to be like in a split second, right, decision. And so if you use this session, you are able to improve, because basically you can use data from that session to improve the way that you're constructing a posterior. And so here at some point I said that I am sampling from the likelihood, which is correct. But we also have methods where we can add a prior to that likelihood, and then it becomes a posterior, and then I can sample from the posterior instead of sampling from the likelihood, right? And so that could be further improved if you're able to capture something beyond the just individual impression and look at it in the vision of a whole session, or even more than a whole session.
So your point is that it's just like a computational bottleneck. If we could do it faster, there is nothing that prevents you to do it, right?
Yeah, but it's not just computational bottleneck. I believe that there may be more information that you gather if you keep in mind the whole session.
Yeah, of course, the whole trace. But the point is that the reason you didn't do it yet is, well, one, because no time, and then two, I guess, because it will make it less fast.
Yeah, and here, like, speed is really paramount.
Right.
And this is the reason why we basically didn't use our standard bandits. Like we have standard bandits. Why didn't we use them?
Right, because the softmax is so fast to sample, right?
Exactly. Like speed is really paramount.
Yeah.
Not just softmax, like even G, like even computing G itself, right? Which is this guy. That too, because things change. Like whenever the user gives you a signal, typically you can say, okay, I can update the next hour. But in this particular use case, you really have to update your priors and posteriors and everything within a split second.
The moment, yes.
Yeah.
Got it. Okay, let's see. In this, I think, was the last question. Yes, this is the last question. Any other questions from my organizers, or? Okay. Yves, any?
I think we could potentially use the next minute or two to move over to the poster session to leave a bit of time for people to log in over there.
Okay.
But yeah, thanks a lot, Wissam. That was amazing. Thank you so much.
Yeah,
thank you,
absolutely. So I will stop sharing, and I will be hanging around the poster session too if anybody has more questions.
Awesome.
Session.
Sounds good. See you all in the poster session.
Bye.
Bye.
داریم؟ کجا؟ حالا وقت نکرده بودیم
نشسته بودیم. چرا انقدر محکم میبندی؟ میخوای به روخم بکشی؟ میخوای بهت نیاز داشته باشم؟ شیرینی های نوری پیسه که بهمون میدی؟ چرا دیگه رفتیم سگ بازی؟
چیزه
چیه؟
In a quarter mile, turn left onto Borden Avenue.
برو دیگه.
Hello.
Hello.
Hello. So, oh, Min Min, is she on the Zoom already? Hi. Hi, Min Min.
Hello.
How are you?
I'm doing well.
Good to see you.
Yes. Yes. Hi, Flavia.
Long time no see. How are you?
Good.
Good. You're doing exactly. It's the same thing what happened to Crito. We're always working on the same subjects.
I
always find your paper like, aha, Min is at it again.
Oh, that means we're at least not going in the wrong direction.
Or together in the wrong direction. That's funny.
How is life? All good?
Sorry?
How is life? It's all good?
Yeah, it's
as good as it gets, I guess.
yes. We got a new baby, so it's a drastic change.
You need to scale up, huh?
I don't know if it's scale up or down.
Exactly. No, scale expectations, yes. Yeah, we stopped at 2. We couldn't. I wanted 4, but 2 it's okay.
Okay, I'm going to try to.
Yeah.
So it should be presenting from my laptop, right? Okay.
Yeah.
Yeah. It should
Yeah,
be
so-
just the share button. And by the way, so I think Maria and Adif are going to chair the session.
Okay.
Maria, do you want to do all the chairing? Like, I'm monitoring the chat and stuff, but do you want to introduce Min and the
Awesome.
rest of-
Okay, let's give folks 1 or 2 more minutes to come over.
It's good.
Kick things off.
Yeah, I saw that Otmane is here. I could not see Gokhan in the participants. So our second contributor talk.
I've seen him in the poster
He
session
was in the
just a little bit
posters.
earlier.
I'll
Yeah.
ping him.
Can you guys see my screen? So I guess I'm new to the Zoom thing. We're using the Google.
Yes, we can see it.
That's good.
You should present if you go in present mode as well. Yeah.
Yes. Is that better?
Yeah,
that's
works.
perfect.
Yeah.
Okay. All right. Let's see.
And thank you so much again, Min, by the way, for the talk.
No, thank you. Thank you for inviting me. It's I have very fond memory of this workshop.
Yeah, you're the only person who spoke twice at the workshop.
Hopefully
I think you
it's not
deserve a
boring.
prize or something.
Hopefully it won't be boring for the audience.
I
No,
doubt
definitely not. Definitely not.
All right.
Plus the audience changes, so.
I think we are ready to kick things off. Welcome back to the third and last session of this year's virtual reveal workshop, and we hope you have enjoyed it so far, and that you will stick around because we have a great lineup of invited and contributed talks. We will kick off the session with our invited speaker, Min Chen, who is a staff research scientist at Google, and will talk to us about new applications on bandits and reinforcement learning for recommender systems. So please take it away, Min.
Okay, thank you. Yeah, thanks for the organizers for inviting me back. I think I can still remember the discussions we were having 2 years ago when I first came and discussed about our work on reinforcement learning for recommender systems. So this work is going to be focusing on actually the more practical aspect of trying to bring reinforcement learning or bandits algorithms to even more problem spaces in recommender systems. Yeah, of course, none of the work would have been possible without all my awesome collaborators in Google. So for recommender systems, I guess our goal is trying to match users with the right content at the right time. And over the years, we've seen the back-end powering these recommender systems evolve from the simple collaborative filtering to supervised learning. And in the last few years, there have been a lot of interest in using reinforcement learning for recommender systems. So over the years, while our team was trying to push for more and more IO solutions in recommender systems, I got asked by people a lot on the questions of, well, what happens to all these good old supervised learning models we have been building for years? Are you going to replace them all? And the short answer is, of course, not. And in fact, these two camps of methods approach recommendation from a very different perspective in our view. So with supervised learning focuses a lot in terms of predictions. In other words, trying to predicting users' responses towards recommendation when they click. Or yes.
Sorry to interrupt. For some reason, we see the bottom of your slides being cropped. At least some of us. I don't know why. Directly through Zoom.
Let's see. So how do I do this?
Maybe try to lower the screen and then increase it again. It solves my problem in the earlier talk.
Lower the screen?
Like making it like a small window and then full window again.
Does this work? No.
Can you try present again? Maybe that was just it. Try to switch to present again. If you could go to slide 4. Slide 4 is a good example because it has text at the bottom.
Okay.
Yeah, and then try present again, just in case that works.
You can press escape to show again the controls. And then
yeah.
Yeah.
No. Is it work?
Yes. No, it doesn't. Again, I think the control bar kind of does something here.
I see. Yeah, no.
It's just a control bar of Zoom, right? Or
no, it's a control bar of the Google Docs, I think.
Could you download the slide locally, you mean, and open it? Maybe not through Chrome?
I think it's the Google Doc viewer that's the problem. Maybe if you could download it as a PowerPoint.
I see. I think my laptop is freezing. Give me a second.
Sure.
Oops. Okay.
I think that if you don't have many slides with text at the bottom for things that are a bit cropped up, you can walk us through it verbally if downloading the presentation with PDF doesn't work.
Yeah, how about I go as is and then
yeah, so you can go as is, you can assume that in this example we see natural fit in the bottom, we see interactions with users and partial feedback, and then that's it.
Or
so
maybe quit the presenter mode and do in the other mode.
Yeah.
With smaller slides.
Exactly. Yeah.
Okay.
Yeah,
Does this work?
That works.
Yeah, if you move the panes like on the left and on the right, you try to squeeze them. Right? Yeah, exactly. And then the one on the left, maybe you can squeeze it a bit more. Or not. Okay. I guess I mean that's okay for me at least. I think that's okay, right?
Yeah, it's fine.
Okay, I think try to go ahead, Min.
Okay.
Thanks a
awesome.
lot. Sorry about this.
No, it's my bad. Yeah, I guess yes. I was at so for supervised learning, it focused on predictions and basically predicting users' response toward recommendations, while reinforcement learning or Bandit, it focuses more on the decision-making part. In other words, trying to come up with actions so that we can maximize some long-term rewards. Well, we can argue that reinforcement learning or Bandits is a more natural fit for recommender systems, because in the end, we are interacting with users. In other words, we have to choose an action. And also because of the partial feedbacks in recommender systems rather than observing the full feedback as in supervised learning. And of course, the sequential aspect of the interaction. But as said, because these two kinds of methods actually focusing on these different perspectives, they are in the end very complementary to each other. And this talk is going to be focusing on actually the intersections of these different methods, and how can we use reinforcement learning to help supervised learning in terms of converting model predictions to decisions, or learning to choose hyperparameters for supervised learning methods. And also I'm going to touch upon how we use supervised learning or use the prediction power of supervised learning methods to address the variance or sample inefficiency of reinforcement learning algorithms. So first, on RL for supervised learning, or using RL to translate supervised learning model predictions to actions. So I'm going to take notification systems as an example. So notification systems is the offline component of the overall user experience for many recommender systems. So the goal of notification is, of course, to notify users of contents that they are potentially interested and to bring the user back to the platform so as to optimize for incremental daily active and reduce opt-out, as well as improve the user satisfaction on the platform. So here's an overview of a push notification system. It has multiple stages as well. So usually the first stage is focusing on generating the notification candidates and identifying the targeting users. And the second stage is the controlling piece where we will be deciding on whether or not to send a notification to the user. And this is the part where I'm going to be focusing here. So the classic approach to notification is to basically convert, to convert this multiple objectives into a multitask model, prediction model, where we will have each task basically predicting users' responses towards the notification. But the problem is once we have these predictions, how can we decide on an action? In other words, whether or not to send the notification. So I think many existing systems relying on various heuristics. For example, we should send a notification if the incremental data prediction is larger than a certain threshold, or we should drop if the opt-out prediction is high. But the drawbacks of these kind of approaches is very obvious. These heuristic rules are very hard to maintain and it's hard to iterate, and it will be very difficult to scale up to even more objectives. And second, it is very sensitive to model prediction shift. So if you were to add new features or change your model architecture, and then you have to basically retune all these different heuristics again, which is definitely not scalable. So what we are proposing here is basically to treat the problem as a Bandit or NDP. So the unique piece here is that we would take the supervised model predictions as a representation of the state, and in combinations with some user features and context. And the action here is basically try to decide to send or drop a notification, and the reward is basically some combinations of the different objectives. And given the formulation, then our goal is basically to learn a stochastic policy to maximize the reward. And we will do that based on the supervised model prediction. So this is the piece where basically we're combining the supervised and the RL Bandits work. And we're going to learn the policy on randomized traffic, where we would randomly send or drop notifications. So a new challenge we ran into in this case was basically the sparse reward. Because in notification system, actually, for example, opt-out or incremental depth, they are actually very rare events. And because we are learning on these randomized traffic, which is a very small slice, so both of these challenges causes a lot of learning instability if we just rely on maximizing the rewards. So in the end, what we came up with to add a regularization to force the policy to be close to some prior policies. And so in summary, what we're doing here is basically trying to maximize the expected reward while penalizing the reward scale between the learned policy and some prior policy. So, and this formulation actually gives us an analytical form for the optimal policy, which is equivalent as you simply regressing the Q estimate of a state action pairs towards the soft reward target. And in the case of binary actions, and if we try to regulating towards a random policy, the optimal policy or the sense probability actually has a very nice interpretations, which will be proportional to basically the lift or I mean the uplift of sending notification versus not. And so we experimented with this approach and compared to basically a baseline production model, which has been extensively tuned by engineers. And we've seen some very promising results, and we're going to basically iterate on this approach. So for the second part, I'm going to touch upon basically how we can use RL or Bandits to personalize hyperparameters for supervised learning models. So I think this is actually connected to some questions people were asking during the panel discussion on, like, for example, how can you personalize explorations for different users? And so we know that actually I mean, there are a lot of different knobs in recommender systems. And in this talk, I'm going to take diversification as an example. So diversity is actually a very important part of recommendations, where our objective is to present a set of recommendations considering both the quality of the item by itself, but as well as the item similarities or interactions. So there are many different approaches people can take to optimize for or I mean to tackle the diversity aspect. So we're going to focus on a simple approach where we model a probabilistic models where basically we assume the reward of the set of candidates will follow a multivariate Gaussian. With the mean indicating the quality of item and the covariance indicating the interactions of different items. So and these parameters are learned based on data. So once we have a model learned at serving time, what we'll be doing is we will choose each item in turn, and given a chosen subset, what we are doing is we find the next item that will maximizes the conditional expected reward. So at serving time, there is basically this hyperparameter, this discounting factor alpha, which actually controls the diversity of the end result. So the question is, how can we choose alpha? And one can also imagine basically for different users and for different contexts, the optimal diversity level can actually be very different. So in other words, how can we also personalize these hyperparameters in recommender systems? So again, we basically convert this problem into a Bandit or MDP, where the state here is the user features and context, and the action here is these different knobs in your recommender systems. In this case, it is the discounting factors, and the reward here is some definitions of long-term reward. So with this formulation, actually the solution is very straightforward. So what we're doing here is basically we take a small slice of traffic and we would basically randomize the hyperparameters on different slices of traffic to observe its effect. And then we would learn an estimate or a Q estimate, which would basically regress that towards the reward we've been observing for different states when given different actions. In other words, different hyperparameters. And then we choose the hyperparameters or the action which would maximize the estimated reward. So again, we tested out this approach in a live system, where again compared to a production model which was tuned, hand-tuned, versus one where we will learn this policy to optimize for different hyperparameters for different users and different contexts. And yeah, even with a very simple contextualization, it gives us a very significant boost over the production model. Now I'm going to move on to the second piece of the talk, which is going to be focusing on how can we utilize supervised learning models for RL. And the work I'm going to be focusing on is basically how can we build a satisfaction critique or a survey prediction model so that it can addresses the sparse reward in reinforcement learning. So for many of the RL agents deployed have been focusing on optimizing the engagement part of the overall user experience. But we know that there's actually a huge gap between what the users engage with and how satisfied they are with their experience on the platform. So for this work, what we want to do is actually shifting our agent towards optimizing for user satisfaction as measured by survey. So in other words, we will be sending out surveys to users to ask explicitly how they will rate their experience on the platform. So there are actually many new challenges that's associated with optimizing for satisfaction rather than engagement. So first, compare with engagement signals, satisfaction responses is actually very, very sparse. So first, for each user, we can only survey a very small amount of items on the platform. And among the surveys we send out, there's actually a very low chances that user will actually respond to the survey. So for the platform that we surveyed, actually there's only less than 2% of response rate. So in other words, there are a huge space of the user item pairs that we don't have any observed user response. So what we're being proposing to address the sparsity issue is basically to build a supervised satisfaction critique, which is to infer the user's response on any given items on the platform based on the data or based on the survey responses we collected on the platform. So another challenge that's associated with survey response or satisfaction is that actually there is a strong correlation between users' response rate and the actual response. In other words, user tends to respond to surveys when they are actually happy or they like the content. So in other words, there is there are latent confounders which influence both users' decision to respond as well as their survey results. So as a result, the survey response data that we collected will be biased. So in order to address the bias in the survey data, what we're proposing here is basically to to supplement the survey, the satisfaction critique with another hat, which will predict whether or not a user will respond to surveys, and use the inverse propensity weighting to actually debias the survey response prediction from the survey response rate. And with the survey, the satisfaction critique, then what we're doing here to shift our agent towards optimizing for satisfaction is that we change the reward function that's used by the agent to be a combination of engagement as well as the supervised satisfaction critique predictions. So as a result, so when we test this agent in live system compared to an agent which is mainly focusing on optimizing for engagement, we can see actually there is a huge boost in terms of the satisfaction, satisfied engagement, while we at the same time decreasing unsatisfying engagement. Yeah, so as a conclusion, I think this talk, if there are only one message you're taking from this talk, that is, there's our reinforcement learning and supervised learning are definitely not mutually exclusive. And in fact, we have many cases where these two approaches can help each other. And for future works, there are, I think, even though I think there are a lot of excitement in terms of reinforcement learning in the last few years, I think we still barely scratched the surface for really making RL ubiquitous in recommender systems. So for example, we need to be able to handle multiple objectives, and the work on exploration or really taking users towards a more aspirational path is still very limited. And there is also the ecosystem or the multiple stakeholders. I think Inba was talking about in her talk as well. That we want to consider as well, using RL to formulate the problems of the different agents in the recommender systems. And of course, there's this interesting part of confounding in recommendation policies. Yeah, I think that's it. If there are questions. Oops.
Awesome. Thank you so much, Min. I think Maya is trying to unmute herself, but
No.
Oh, perfect. Awesome. Sounds good. I'll leave it to you.
Thank you, Min. This was great. I have one question. I will start with one question. But given that, as you mentioned, there is high correlation between the response rate and also the rating itself, how is the extrapolation bias handled when there is part of the covariate space that is not observed, and then the unsupervised learning is used to basically extrapolate to that space? Wouldn't that introduce a large degree of bias?
Yes, so that's basically what we have been doing here is to use the inverse propensity weighting to address this I guess this problem of we are only observing, or we are observing more of the survey responses on the users who are more likely to respond. So in the sense, it is a doubly robust estimator. So if the regression model is correct, or if the propensity estimate is correct, then we will be unbiased the estimate. But if there are cases where in certain regions of the user and item pair or the state action space where we never observe there's no support, then yeah, that's definitely the case where we won't be able to have a good estimate. So I think there's also some interesting work. For example, how can we utilize the variance or the uncertainty of our estimate, try to influence, like for example, how you send out surveys. If we observe there are certain regions where our estimate is less accurate or less certain, we can try to see if we can send more surveys to solicit more responses.
Got it. Makes sense. Another question from the audience is the reinforcement learning notification controller more maintainable than the previous heuristic rules? And does it handle prediction distribution shift more robustly?
Yeah, so that's actually the hope that so if because I guess the high level idea is that once the different objective of the notation system, once they are prioritized, then as they are encoded in the reward for the agent, then if the underlying distribution of the model prediction changes, that corresponds to basically the state space kind of shift distributions. But because we are learning this mapping from the state action pairs towards the reward, so even if the distribution changed, we can still basically fit different functions towards the reward to optimize the reward. So hopefully that's more robust to distribution shift. So that's actually so after we've seen this result where basically we were able to beat the system which is hand-tuned, and it is very stable. So we have been training this agent continuously over time. And we've seen actually the performance was quite stable over time, and it's actually very trending up. And the next thing we're going to test is basically we're going to introduce some new features and some big change to the supervised learning model prediction, so that it can actually produce this like a large shift into in terms of the predictions, and see if our system in that case can still robustly learn a good policy in terms of sending or not sending notifications.
Thanks. And while our next speaker is setting up, I think we have time for one last question. But please let me invite the next speaker, Jochen Kapan, to set up his presentation while I'm asking this last question. So with a good satisfaction critic, is it still necessary to use another reinforcement learning controller, or can we directly plan using the critic, for instance, greedy or few-step look-ahead planning in a model-based RL approach?
Yeah, that's a very good question. So I mean, if I think it's related to the question that Maria was asking, or like the first question. So if we have like a good reward function for the entire state action space that we are planning, and if we have, of course, like a very accurate dynamics model, then of course you can fully rely on these two components to do a model-based RL to plan. But I think both are a very big if. And we know actually, because especially for satisfaction estimation, given that we observe so little in the entire state action space, I would guess the estimate on like unobserved state action pair is very poor. So relying on the policy optimization component to control where where the critique needs to be accurate is actually very important in my perspective.
Thank you very much, Min. This was an awesome talk. Thank you for joining us. And next, we have Johan Keipan from RecSys University, who will present the empirically loose choice model for learning from interactions. So please go ahead, Johan.
Yeah, thank you, Maria. I'm going to go full screen. Please let me know if it doesn't work, okay? Is it good? Okay, awesome. Thank you. So I'm going to describe a probabilistic construction for inclusion in recommender systems.
So Johan, it hasn't gone to full screen yet. We can still see the slides on the left. Present.
Right. So did I change the slide now?
No.
Oh, okay, give me a second.
Okay. I think that's full screen now. You can?
Now?
You there?
Yeah, I hear you.
Ah, okay. Okay, we thought we lost you for a moment. Now it's full screen.
Okay, sorry about that.
Thank you.
And I can change the slides, right?
Yeah, that works.
Okay, awesome. So I'm gonna talk about the probabilistic construction, the Dirichlet-Loos model for inclusion in recommender systems, and specifically for implicit feedback recommender systems. And this is motivated by the fact that recommender systems learn in a feedback loop, and this is due to interactions with their users, where the user choices from what is recommended by the system is from what was recommended by the system in the first place, right? So the user choice are usually from the recommended alternatives, and this suggests a systematic exposure to the alternatives. For example, the system might have hidden some alternatives and inconsistent preference estimates, and they can also impose undesirable biases. For example, they can unfairly underestimate underrepresented content, and they can overestimate overrepresented popular or promoted content. They can lead to a self-reinforcing feedback loop, which might even cause that the user's interest to degenerate. So what we propose here is that is to understand what would happen if we explicitly incorporate the user's limited exposure to the systematically presented alternatives in the inference of their preferences. So this talk is going to be about the Dirichlet-Loos choice model, which is, as I said, a probabilistic construction for inclusion in recommender systems. I'm going to talk about the properties of the model, and then I'm going to talk about the extension of the model, which would be a Bandit algorithm for online learning to recommend. And there's going to be a set of results on some synthetic performance experiments. And also there's going to be some illustrations on how this construction would eliminate some of the biases that recommender systems are known to be prone to. So let me set this up first. And I'm going to start with the interpretation of implicit feedback as multinomial observations. So this is an approach that has recently gained traction. I think two major papers here are, one of them is the YouTube recommendations paper, where we all describe the recommendation as a classification task, as a huge extreme multi-class classification task, and also the variational autoencoders for collaborative filtering paper, where there's a generative model which uses multinomial likelihood. And so we take that and we extend this to this multinomial to restricted multinomial, which means the choice, the user choice is not made among all the alternatives, but is made from a small subset of alternatives that is presented to them. And finally, we assume this assumption can be based on a very old idea, which is principle of least effort, and which means the user would conveniently choose from what is presented to them, unless what is presented is too unsatisfactory. And we finally assume the independence of irrelevant alternatives, which means the relative preferability of an item to another is independent of the other items that are included in the recommendation or that are absent from it. And this results in a restricted multinomial likelihood, which extends the usual multinomial, which is the first equation here, with this additional term where we have where we're dividing with the probabilities that are included in the presentation set. This conforms to Luce's choice axiom, which is presented in 1959 in his individual choice behavior article. And the setup here is that we have k options, and the probability of choosing one of these options is represented by a vector of theta, and we have subsets of alternatives that are presented to the user, which is shown by this C here, and yk is the number of times option k was chosen and mused or presented. And after getting this restricted multinomial and extending the multinomial model for implicit feedback to restricted multinomial model for implicit feedback, we put a prior distribution to the vector of preferences theta, and which is actually a generalization of the Dirichlet distribution. And this distribution is parameterized by pseudo counts of choices and pseudo counts of presentations, and it is actually conjugate to restricted multinomial observations. This density was actually recognized by Dickey in 1983, and it was also used in a similar applications. Of course, we didn't have recommender systems back then, but there were similar ideas, for example, censoring the observations and guessing what was censored. And this model, of course, reduces to Dirichlet multinomial, which is familiar if the choices are made from the whole set of options. And so there are nice properties of the model, which I'm going to talk about briefly. And one of them, I think a fundamental of them is the independence of unexplored options, which means which means the preference estimates for the options that were never presented stay invariant, and this is independent of other choices made. This is very much different from the Dirichlet multinomial, because in a multinomial likelihood model, every choice actually imposes negative bias and actually imposes negative bias to every other option. Here, this is not the case. If an option was not presented before, it's not going to be penalized. And this remark actually extends to groups of options, new options that are cold started to the system, which means the cold start items are going to be treated equally. There's another property of handling of cyclic choices. So if you look into the actual equation carefully, you would see that the likelihood and the posterior actually ignores the particular associations between choices and presentations. This is an unfortunate case for handling cyclic choices, because the model confuses cyclic choice with a tie, which means if you prefer, for example, A to B, B to C, and C to A, this is interpreted.
I think we lost you. You can? You hear us? Let's give Johan a couple of seconds.
Let's give him a little bit of time. Otherwise, Maria, you'll have to do the rest of the slides.
Hello?
Oh, hi, you're back.
You're back. Good.
Slides. You hear me, right?
Yes, now we can hear you.
Okay. So in handling of cyclic choices, the model actually treats cyclical observations as ties. This means if you prefer A to B and B,
Johan, sorry for interrupting. The audio quality doesn't come through. Johan, if you can hear us, could you please turn off your video because the sound doesn't come through, so maybe it's a bandwidth problem. Why don't you try to turn off the video to see if that works?
Yeah, apologies.
We can hear you now. We can hear you, but to be on the safe side, let's turn off the video to make sure it won't freeze again.
Should I stop recording?
Yeah, stop the video, but don't mute. At the bottom. Okay.
Yeah, of course.
We can hear you. But please share your screen again because we lost your slides.
All right. So you now see them, right?
We can see them. All right. And full screen present mode, please.
Hello?
Yeah, we can hear you again, but unfortunately we lost you before.
Okay, is it in full screen now?
Now it's full screen. Hopefully it won't lag again.
Okay, yeah. And let me look quickly. And now we can talk about. So if we look into the distribution of preferences, we see that it is parameterized by something that is actually that actually seems quantums, which are going to be sets, which is obviously infeasible to deal with. But the inference actually can greatly benefit from the sparsity of this statistic mu, and this is because majorization, minimization. It says if you build a graph where the edges are, whether the items are recommended together, and if this graph is connected, you're good.
Johan, unfortunately, the connection is.
You can learn. You can learn preferences fairly efficiently.
Johan, the connection is still very laggy, and we can.
For example, you can pick a pivot option.
Johan, if you can hear us, the connection is very laggy, and we'll have to move on to the next speaker and leave some time at the end for people to engage with you.
With the other options
Gather now.
you can collect feedback,
Johan cannot hear us.
and then you're gonna get.
Try to mute and doesn't work. Oh, maybe it works.
In the meantime, I will invite our next speaker to set up the slides. Our next speaker is Otman Saki, who is a researcher at Criterion, and will talk to us about improving offline contextual bandits with distributional robustness. Johan, if you can hear us, we will move on to the next speaker, and we will conclude a bit earlier so that people can engage with you for your paper in GatherTown, because at the moment the connection is very laggy and the presentation doesn't come through.
Yeah, I heard you. Yeah, we can do either way.
All right, so we'll move on to the next speaker, and please, we invite the participants to engage with Johan and his very interesting work via GatherTown. In the end, we're going to conclude a bit earlier. So let me introduce our next speaker, our last speaker for the session, and this is Otman Saki, who is a researcher at Criterion, and will talk to us about improving offline contextual bandits with distributional robustness. So please go ahead, Otman.
Thank you, Maria. So I'm Otman Saki. I'm a first-year PhD student at Criterion AI Lab in the recommendation team. And in this presentation, I will be presenting you a way to improve offline contextual bandits with distributional robustness. And this is actually a work with Louis Faury and Flavien Vazil, who are great colleagues from the recommendation team. In this presentation, I will be trying to present the contextual bandit framework in general and the offline contextual bandit optimization in particular, and how prior work tried to treat this problem. Yeah, sure.
For some of us, I think at least the slides are not showing.
Okay, don't you see
maybe
the
in
table?
Cobalt they're showing, but if we're using, at least I'm using the direct client and it's just a black screen. Now we can see it when you go into presentation mode. For some reason, maybe you have two displays.
I'm sorry, display read mode.
Try again full screen, let's see.
Okay.
Let's see what happens.
Can you see it?
Nothing changed for now. I think it's displaying on a second screen, maybe, I don't know.
Maybe if I do just this.
Yeah.
Oh, it works now. Yeah.
We can see it now.
Yeah.
Oh yes, that works. If you collapse the other panes, that works.
Okay, perfect. I'll leave it like this then. Yeah, maybe I can make it full. Now it works well. Perfect.
Yep.
Okay, nice. So I'm gonna present the framework of contextual bandit and its offline formulation, then just talk about prior work on how people treated this problematic before and the identified challenges, then present distributionally robust optimization as an alternative to prior work, and see how we can leverage it for to deal with these challenges. And then I'm going to present the experimental setting and the preliminary results that we got. So for the contextual bandit problem, it's this sequential decision problem where we have at each timestamp context that we interact with and a system that that is here modeled as a policy that proposes an action and for this context, and it gets a cost. And in recommendation, for example, the context might be user features, And our system is a recommendation engine, which recommends, for example, some items, and we get a click or non-click or sale or non-sale as the costs. And our goal here is to find the best policy that minimizes a risk, which is just the average over all of the contexts that we encountered of the costs. And its offline formulation is when we have to do this search of the better policy offline using some logged interactions between our system and the users. And to do this, we have the user features, the actions done, the costs gathered, and then we also use the propensity score, which is the probability of, under the current system, of doing action A conditioned on the user feature. And of course, as we don't have access to the real risk, we always use an estimate, an empirical estimate based on this logged Bandit feedback or Bandit dataset. And the commonly used estimator is the inverse propensity score estimator, which is just defined by importance sampling. So you have pi on pi 0 multiplied by the cost. And as everyone knows, the inverse propensity score estimate has high variance depending on the disparity between the policy that we want to test and the login policy. So if they're close, everything is fine, and this estimate has really a low variance. But when we need to test policies that are far away from the login policy, we get an estimate with high variance, and it's not reliable at all. So to optimize this, Adith and Thorsten proposed CRM, which is counterfactual risk minimization principle, that is based on a risk or a variance penalization of the risk. So instead of optimizing the empirical risk directly, we try to optimize the empirical risk penalized by the variance. So we transform the problem of trying to find the best policy that minimizes the risk to a problem where we try to find the best policy that minimizes the risk but doesn't induce high variance on the empirical estimate of our risk. And it has been shown in their paper that this objective have better statistical properties, but we identify like 3 main caveats. So the first one is it induces a harder optimization task. So whenever we add this variance penalization, we break convexity of the objective with respect to the policy. So using the empirical risk alone doesn't break this convexity because the empirical risk is just linear on the policy. But when we add this square root variance, empirical variance, we break this convexity, making the problem harder to optimize. The second issue with this objective is that there is no algorithm that can leverage stochastic gradient descent, so it's not scalable at all. And even a variant that was proposed in the first paper that introduced CRM needed to load the entire data sets at the end of each epoch to do the optimization. And the third one is that we have no method to set the lambda, the hyperparameter, automatically. So we have always to go through cross-validation. It becomes really resource heavy, and in this work we try to leverage distributional robust optimization, which is a framework that can address these challenges. First of all, I'm going to just introduce some notations. So phi here is a real valued convex function, and phi star is its Fenchel conjugate. Phi refers to the F divergence associated to phi, and the vector 1n is the vector in Rn with entries all equal to 1 over n. So it's in the n-dimensional simplex here, noted by delta n. And you can see here that delta n can be just interpreted as distributions with a finite support. So there is an equivalence between delta n and distributions with a finite support. And how the distributional robust optimization defines its robust risk. Here we have the robust risk based on a divergence is defined as follows. So it's the supermum over distributions with finite support that are not far away from the empirical distribution. And with these distributions, we compute here the average. So it's kind of a reweighting of our data points, a reweighting of the loss. And this reweighting shouldn't be far away from the empirical or the uniform reweighting based on this phi divergence. And here we set epsilon to have an upper bound on how far these distributions are from the empirical distribution. So to give intuition, for example, if we set here epsilon to 0, the only distribution that satisfies these conditions is the empirical distribution, and qi will be equal to the vector 1 over n. So here you'll end up with just the empirical risk. And if we set epsilon to plus infinity, for example, here, the sub here, or the maximum, will be over all of the distributions. So imagine if we had one huge loss here for one observation, all of the mass will be put there. So you will have 1 for this particular observation and 0 everywhere. So this becomes a it's like optimizing the maximum over your loss function. And it happens that this robust risk is actually equivalent asymptotically to the CRM principle. So it decomposes into an empirical risk plus a variance penalization term plus some terms that vanish asymptotically. So the idea here is that in some sense, DRO generalizes CRM. And here, what we said so far is DRO is a good framework that can be an alternative to CRM, but the real question is, what can it bring to the table? So the first thing is that when we want to minimize the robust risk, we can leverage its dual formula from convex optimization, and we get that this robust risk is equivalent to minimizing another function, which is called here G, and it happens that this function is convex with respect to all of its arguments. So DRO transforms the CRM problem into a convex problem with respect to pi, beta, and gamma. So that's the first thing. The second thing is that as these problems are equivalent, we can see that G pi here is composite. Composite meaning that it decomposes into a sum over all of our observations. So it can be optimized by all of the stochastic gradient descent methods that we know so far. So there is no need whatsoever to load all of the data set versus all of the stochastic algorithms that were proposed before. And this is kind of new in the CRM principle. And the third contribution is that we can set epsilon, which is the hyperparameter of DRO, with asymptotic arguments. And we don't really need any cross-validation for it or to set it. So we have an automatic calibration for this hyperparameter based on asymptotic coverage arguments. So when we set epsilon to this value, which is phi prime 1, multiplied by p square quantile over 2n, we can say that with high probability, the robust risk will eventually cover the true risk with enough samples. So we have here a hyperparameter free method, which is, of course, resource friendly here. What we said so far is that DRO can generalize CRM. It's convex on pi, SGD-able, and with automatic calibration of its hyperparameter. So let's see the experimental results. For the experimental setting, we employ the classical multi-label to Bandit conversion method. And it's all described in this graph here. So if you have any multi-label data set with a train set and a test set, you take the train set, take a fraction of it, and train a policy on that fraction with supervised learning, so you have access to all of the labels. With this policy, you do the following. You go through all of the training set, and for each context, you sample an action from your policy and compute the cost, which is the Hamming loss between the action sampled and the true label. And you do this 4 times. So you end up with a Bandit data set, which is 4 times bigger than the trained data set that you had before, with context, actions, costs, and propensities. So you built a Bandit data set from this multi-label data set. And with this data set, you split it into a train test, into train vol, sorry, and you run your favorite algorithm to train a policy with different hyperparameters. You select the best hyperparameter on the validation and then test it directly on the test set to get a risk for the policy and a risk for the greedy policy derived from that, which just, instead of sampling, just recommends or chooses the action with the highest probability. And of course, for the robust risk, in general, we have to specify a phi divergence. And there is a huge catalog of phi divergences that we can use. But in these preliminary results, we used 4 phi divergences, namely chi-square, KL, Berg, and Hellinger. And they are defined in this table below here. And they can either be defined by the divergence or just the phi associated. And in our results, we only trained for all of the algorithms linearly parameterized policies. And the lambda hyperparameter of POEM, POEM is an algorithm that is based on the CRM principle, is set by cross-validation. So the lambda, that is the weight of the variance penalization, is set by cross-validation. For DRO, we set epsilon to its recommended asymptotic value. So there is no need for cross-validation whatsoever. And we use LBFGS for the batch setting and ADEM for the stochastic setting. And here for now, we just only use 2 data sets, which are SEEN and DEAST. And we compare POEM to DRO in both batch and the stochastic setting. And we can see that there is some slight improvement brought by the DRO in terms of risk and greedy risk, and in terms of like stability as well here. Because for instance, POEM has a bigger standard deviation than DRO in both settings here. And you can see that as well on the yeast data set. For the stochastic setting, however, POEM has a stochastic version that is based on a majorization minimization algorithm. It uses stochastic gradients, but at each end of epoch, it needs to run over all of the data set to compute some statistics. So if you have really big data set, you can't really scale this algorithm to it. So, but we can compare POEM S, poem stochastic to DRO stochastic, and we can see that poem stochastic has better results, but DRO can still be comparable even if it's unfair for DRO. So far, we said that DRO can compete with CRM without hyperparameter tuning. DRO stochastic is the first fully stochastic optimization algorithm that minimizes this variance penalized objective, contrary to poem stochastic. And we also observe faster training time for DRO in the batch setting. We need to investigate this more, and of course we'll have tables for it in the full paper. Okay, so let's recapitulate. Here we identify 3 main caveats of CRM and leverage DRO to propose a better optimization task, a fully stochastic optimization algorithm, and a method to automatically calibrate the hyperparameter. And of course, this is still an ongoing work, so we still need additional experiments to confirm DRO's improvements or not. So we need to try with different login data, login policies, sorry, which are more deterministic. Of course, experiments on bigger data sets and experiments with other estimators than IPS, and also maybe experiment with different phi divergences and see their what can they bring really into the table. Hope it was fun for you to follow, and thank you very much for your attention.
Thank you very much, Adnan. This was a great presentation.
Thank you.
And we have time for a few Q&A.
Sure.
So one question is that optimizing the inverse propensity score estimates typically need the inverse propensity weights to be clipped in order to produce reasonable optimization problems. Does a robust risk avoid this clipping?
That's really a nice question. What we do is not really clip the estimate, but in the optimization process, we clip the gradient for both optimization for both algorithms to keep them comparable. But we need to try clipping the propensity weights as well. And the main problem with clipping is that if you don't have costs that are negative, it will break that convexity that we claim about the policy. So for now, we just need to, we wanted to compare POEM and DRO in the case where we only clip the gradient. And afterwards, we're gonna surely compare them with a different estimator, for example, clipped IPS or maybe doubly robust IPS or like any other estimator.
Yeah, this was my follow-up question. How does the method compare like with doubly robust approach or even like iterations on top of doubly robust where there is some bias introduced to reduce the variance, and basically we select the amount of clipping by solving a convex optimization problem there?
Well, there is this paper by Thorsten as well, where they try self-normalized IPS, and afterwards they add variance penalization, and they see that even with an improved estimator, you can still have additional improvement with this variance penalization term. So we expect that even if you use any other estimator, using it with the DRO framework might be a good way, or I would say a free way to improve it.
And a very related question to that is that IPS is not reward invariant, and CRM was shown to be vulnerable to propensity overfitting with weighted IPS, self-normalization IPS proposed a fit for that. And does DRO offer a principal alternative?
I think it will suffer from the main caveats than the CRM, because in both cases, all of these caveats I think, depend on the estimator that you use and not on the objective that you're optimizing for. So IPS alone will always suffer from this. But for example, if you use doubly robust, for example, doubly robust is not reward, well, it's reward invariant, and so as, for example, self-normalized. So you will, all of the gain that you will have from different estimators can't be really, how can I say, can be dealt only by DRO. So you have to change your estimator and you add DRO on top just to try to improve the optimization process. But I think that the estimator itself is as important as the optimization process.
The final question was, how does the training performance compare between DRO and POEM?
The training performance in terms of accuracy or the training time? So in terms of accuracy, we saw here pretty much similar results with slight improvements for DRO. But in terms of training time, well, I didn't have the tables yet, but I see a really huge improvements on the training time. Because, for example, POEM stochastic needs to do twice as much evaluations as DRO, because it needs to go through the data set twice to compute system statistics and do the optimization. And even in the batch setting, LBFGS converges with less iterations than when using POEM alone.
Makes sense. So thank you, Otman. This was awesome work. Thank you for presenting.
Thank you very much.
And I have a few remarks before we move into the closing thoughts. Regarding the talk of Johan, I would encourage you to visit poster 7 on GatherTown. This is, hopefully GatherTown is still up and you can have some engaging conversation with Johan when he can present a very interesting work. He did, and also we have asked Johan to record his talk, and we will be uploading it to the Reveal website, so you can also see it there. So, all right, this is at the end of the third and final session of Reveal. We had a record number of participants this year, so thank you all for joining us for this virtual event. I think it's going to be memorable to all of us, and we hope we can meet you in person to next year's Reveal in RecSys. So do any of the organizers want to have any other closing remarks?
No, just happy that it all went fine, or 90% fine. And thanks everyone for attending and staying so long and so late. And hopefully we'll see you next year in Amsterdam.
Next week. That's optimistic.
It's just wishful thinking, I think. It's a Freudian slip. But no, next year. Yeah.
Time flies. Time flies. Time flies. Just a week. All right. Thank you all.
We should probably also just commit to, like, I think the website is going to be updated, right? Once we have the slides from our invited speakers, or once we know where these recordings are going to be available in a few weeks' time, we'll have links to that on the website. We should just come back to the website to see those.
And one thing I want to explore with Johan as well is to, because we didn't get to see the last part of his talk, so maybe recording the talk and putting it available on the website as well. So we'll explore to make sure that people have access to it after the conference.
Yeah, okay.
Okay, well.
All right, that's it. Thank you so much, everyone.
Thank you.
Bye.
Thank you. Bye-bye.
Bye.
Bye.
Thank you, guys. It's an awesome workshop, as always.
Bye.
Thank you, Tao.
Bye. No.
Bye.
Bye.
All right, I'm going to stop the recording.